Hello, friends, and welcome back to the Snoozy Scientist, where we gently wander through the mysteries of science, one sleepy yawn at a time. Tonight, we are traveling to the farthest edge of our planet, to a place where the known world gives way to silence, a realm so deep and so uncharted that even our most advanced machines return with more questions than answers. Far beneath the surface of the Pacific Ocean lies a trench almost 7 miles down, a place colder than distant moons and darker than any night we have ever known. Here, the weight of the ocean presses with a force that bends metal and erases light, shaping a world that feels both ancient and untouched. Scientists have mapped the surfaces of Mars and the Moon in exquisite detail, yet whole regions of this trench remain unseen. As descents push deeper, machines begin to falter. Cameras dim without warning, sensors drift, and robots vanish into the dark as if swallowed by the water itself. The chemistry here shifts into something unfamiliar, the water growing denser and colder, guiding life into forms that stretch what biology can endure. Strange low whispers echo through the deep, sounds that cross entire oceans and hint at hidden movements along the trench walls. Somewhere in these depths, the familiar rules of engineering begin to bend, reshaped by a pressure so immense that 16,000 pounds press upon every single square inch. Metals flex, spheres strain, even the strongest designs shrink against the weight of a world that has never needed to accommodate us. And in the midst of all this, life still finds a way to survive, quiet and steady, shaping itself into something almost unrecognizable. But why does this vast place remain so unmapped? What hides in the blind spots that our instruments cannot reach? How does pressure reshape both matter and life in ways we still struggle to comprehend? And why does the deepest place on Earth seem to resist even our most determined attempts to explore it? Tonight, we are traveling toward a frontier that sits not in the stars, but in the silence beneath our own oceans. But before we begin, if you enjoy these journeys, gentle, soothing, and quietly filled with wonder, I would be grateful if you gave this one a soft like and perhaps tapped subscribe. It helps other curious dreamers find their way to this peaceful little corner of the internet where science and sleep meet. And if you would be so kind, let me know in the comments, where are you listening from tonight and what time is it where you are? It is always a joy to see how far across the world this little sleepy corner of science travels. Now take a slow, deep breath, let your shoulders loosen, and together let us drift softly into the mystery beneath the waves. Far below the gentle sway of waves, beneath storms and drifting currents, and all the light that ever touches the sea, the world begins to fold into itself. The surface feels calm from above, yet the planet carries older stories underneath, stories written not in water or wind, but in the patient movement of stone. The Mariana Trench is one of these stories, a place shaped not by chance, but by the slow choreography of the Earth's crust. To understand its presence is to look past the water and into the bones of the planet itself. The seafloor is not a single unbroken sheet. It is a mosaic of giant plates, each one drifting at a pace so slow it almost feels still. Yet over the span of ages, these plates reshape entire oceans. In the vast reaches of the Pacific, one of these plates glides steadily toward another, the heavier one sinking into the mantle below. This quiet descent is known to science as subduction, although it feels less like a fall and more like a long and deliberate surrender to the deep interior of the Earth. Where the Pacific plate slips beneath the Philippine plate, something remarkable forms. The seafloor bends downward, folding like heavy fabric, creating a steep and narrow scar that stretches for many hundreds of miles. It is a place where the crust is pulled tight, where gravity guides rock into a trench that seems to reach for the center of the world. Over tens of millions of years, the motion continues, steady and unhurried, deepening the cut and sharpening its edges. With each passing age, the trench sinks a little farther, responding to forces that never sleep. If one could drift beside it, suspended in the cold, dark water, the shape would appear almost unreal. The walls rise sharply, leaning inward like two immense slopes pressed close together. They form a V that narrows as it falls, guiding everything toward a floor so thin and stretched that it feels more like the shadow of a valley than a valley itself. The gradients here are extreme, plunging faster and deeper than nearly anywhere else in the ocean. It is a structure sculpted by pressure, gravity, and the slow tug of subduction, a design created not by intention, but by the physics of a restless planet. Soft sediments settle along the walls, carried by centuries of drifting particles. Some cling to ledges, others cascade downward in slow-moving clouds. Beneath that layer of silt lies a frame of compressed rock, bent into angles that betray the strain of entire continents in motion. No sunlight reaches these stones, yet they hold a memory older than any light could show. The trench is not simply the deepest point on Earth, it is an archive of the planet's ceaseless motion, a reminder that even the most silent places are shaped by forces far beneath them. Within this long scar lie several depressions, each one a small pocket where the seafloor dips deeper still. Together they form what explorers have come to call the Challenger Deep. It is not a single pinpoint, but a cluster of hidden basins, each separated by rises in the seafloor that sit only a little higher. Over time, careful measurements revealed this quiet complexity. Instruments lowered from ships traced the contours like hands feeling the folds of fabric, discovering that the deepest point is not a single spot, but a scattered pattern of pools. These pools shift slightly with new readings, not because the Earth changes quickly, but because measuring such depth is a delicate act. Sound bends under pressure. Sensors adjust to cold, dense water. The floor is uneven, shaped by sediment, rock, and the tugging motion of the descending plate below. Each reading adds another thread to the picture, and still the picture is never fully complete. What appears to be the deepest point today may be surpassed by a shallow dip near it tomorrow. The Earth hides its details well at these depths, revealing them only in fragments. If one could hover above the trench floor, the space would feel impossibly narrow. The walls loom like distant cliffs seen through a world of suspended darkness, and the floor stretches out in a thin ribbon of sediment that has traveled here over ages. Gravity presses in from every direction, not harshly, but with a steady and ancient weight. It is the kind of place that feels carved by time itself, shaped by no human hand, and indifferent to human curiosity. Above all else, the trench is a meeting point. It is where stone meets stone, where the surface of the earth gives way to the interior, where the past meets the present in layers of rock that sink slowly toward heat and pressure far below. The water may hide it, but the trench remains a monument to motion, formed by plates that drift quietly across the globe. As we move forward, the water around this geological scar will grow colder, denser, and darker. The forces that created the trench continue to shape every inch of it. The Challenger Deep waits within these folds, a reminder that even the most dramatic features of our planet are formed slowly, patiently, and often far from human sight. As the story of the trench deepens, our view shifts from the shape of the Earth itself to the tools we use in an attempt to understand it. Long before a machine ever touches the seafloor, exploration begins with sound. Ships drift across the surface, sending pulses downward like gentle taps on an unseen door. These pulses travel through the water, bounce from the bottom, then climb back upward, carrying hints of what lies beneath. It is one of the oldest methods of peering into the dark, born from the idea that sound can reach where light cannot. For much of the ocean, this approach works well enough. Above shallower plains and slopes, the returning echoes form smooth and faithful silhouettes of the world below. But as the water thickens, cools, and deepens, sound behaves less like a beam of clarity and more like a wanderer unsure of its path. The deeper a pulse travels, the more the ocean reshapes it, stretching it, softening it, bending it away from where it was meant to go. Imagine a world of cold brine where pressure builds with every step downward. At 6,000 meters, the weight becomes so immense that even the water itself changes character. Molecules pack closer together. Temperature falls to levels that slow the movement of everything, even sound. These conditions form a realm where the rules shift quietly. A pulse sent downward no longer travels in a clean, predictable line. It moves through layers where warm and cool currents drift like invisible rivers, where dense pockets of water guide it off course. Pressure squeezes sound until it travels more slowly, spreading its energy over longer distances. When the pulse finally reaches the seafloor and returns, the signal is weaker, stretched thin by the journey. It arrives not as a sharp reflection, but as a fading memory, blurred by the many layers it passed through. Reading that echo is like trying to understand a sentence spoken through miles of wind and stone. These distortions affect even the most advanced forms of mapping. Multi-beam sonar, a system that sends out fans of sound across wide angles, attempts to gather thousands of depth points at once. In shallower waters, these fans create maps detailed enough to reveal valleys, ridges, and gentle curves with surprising clarity. Yet as the depth grows, the fans widen too much, losing focus. The beams scatter slightly as they descend, and by the time they return, the information they carry is softened beyond repair. Below 6,000 meters, where the Hadal world begins, the limits of sonar reveal themselves in earnest. Here, mapping the seafloor becomes an act of patience. Each pulse takes several seconds to travel down and back again. A survey that might take a day in coastal waters can stretch across weeks in the trench, and still the result remains a mosaic of approximations. Instrument noise blends with natural background sounds, and reflections from steep walls return at odd angles, creating shadows in the data where entire regions appear to vanish. Cold brine, denser and heavier than the water above, acts almost like a veil. It slows the pulses further, as though absorbing pieces of them. Sound that should travel in a straight path begins to bend downward or sideways, guided by gradients of temperature and pressure. Mapping software must guess how these distortions behave, yet the ocean rarely conforms to our predictions. A shift of a degree in temperature or a slight change in salinity can alter the path of a pulse by many meters. The trench's steep V shape adds another challenge. Sound striking an angled wall reflects away from the ship, never returning to the sensors. This creates long stretches of missing information, like pages torn from a book. The narrow floor hidden between towering slopes becomes especially difficult to trace. Even when the pulse reaches it, the return signal may be too faint to interpret. Some points appear shallow when they are deep, and others seem deep when they are only ledges on the wall. All these distortions accumulate, stacking gently on one another. The final map becomes a tapestry woven from approximations, each derived from echoes that have traveled through a world constantly in flux. A single line may look smooth, but when thousands are placed together, small uncertainties grow into broad blind spots. Entire pockets of the seafloor remain unresolved, hidden not by darkness, but by the complexity of the water above them. Explorers know these limitations well. They study each anomaly, each faint return, each uncertain boundary. The goal is not to force precision where the environment resists it, but to trace what can be traced and accept the parts that remain unknown. Sonar, for all its sophistication, was built for a world of predictable paths. The Hadal depths, shaped by pressure and temperature and restless geology, are anything but predictable. As the ship moves across the surface, the ocean below carries on in its quiet, shifting way. Sound pulses continue their long descent, touching the unseen floor and drifting back through the cold layers. Each echo is a reminder that some places reveal themselves only a little at a time, shaped not just by how deeply we look, but by how carefully the world allows us to. As we drift deeper into the story of the trench, the world around us grows heavier in ways that are difficult to imagine from the surface. Water, which feels so light against the skin, becomes a force of staggering weight as it gathers above itself. Every meter adds a little more, and every 10 meters adds the pressure of a full atmosphere. It is a quiet accumulation, steady and patient, the ocean pressing inward from all directions as if sculpting whatever dares to enter its domain. This rise in pressure is a natural consequence of depth. Each layer of water holds the weight of the layers above it. Near the surface, this weight is gentle. A diver can swim through it with ease. But as one descends, the weight grows, gathering strength until it becomes a kind of invisible architecture, building downward instead of upward. At 1,000 meters, the ocean presses harder than any storm felt at sea level. At several thousand, the force becomes enough to deform metal and challenge every idea engineers have shaped into vessels. By the time the trench begins to open below, pressure has risen to levels almost beyond comprehension. Near the deepest points, 16,000 pounds rest upon every square inch, a load that would flatten concrete and shatter steel. The ocean at such depths behaves less like water and more like a silent, crushing presence. Every object is tested, every surface is examined. Nothing escapes the slow push of this immense force. Metal, which feels so solid in the human world, begins to reveal its vulnerabilities. At great depth, the structure of metal is strained, molecule by molecule. Tiny imperfections, invisible on land, become potential weaknesses under the enormous weight. Engineers call this fatigue, a slow wearing down that occurs when a material is forced to bear more than it comfortably can. A sphere of titanium may seem impenetrable, yet as pressure climbs, even it begins to whisper under the load. The walls of a vessel may thicken, shapes may be refined, but the ocean never stops pressing. Real moments in deep-sea engineering have shown how unforgiving the depths can be. There have been vessels that descended with confidence, steady and well-built, only to meet conditions they could not withstand. In some cases, the collapse is so sudden that it completes in a fraction of a breath. Metal walls fold inward, not gradually but all at once, as though the sea simply decides the structure no longer belongs there. These events are rare, yet they remain etched in the memory of ocean exploration, reminders of the fine line between success and the immense power of the deep. The physics behind such collapses is straightforward, though the reality feels anything but simple. Pressure acts evenly in all directions, a quiet and relentless squeeze. Any weak point, no matter how small, becomes the first to give way. When it does, the surrounding pressure rushes in instantly. The collapse occurs with enormous speed because the ocean does not need time to gather strength. It already holds all the strength it needs. To survive in this environment, engineers long ago discovered that certain shapes fare better than others. A sphere, smooth and even, distributes pressure across its entire surface. There are no corners to concentrate force, no flat panels to bow inward. The shape is elegant by necessity. It is as close to perfect as a human design can be within such an unforgiving world. Yet even a sphere is not flawless. It relies on material purity, uniform thickness, and careful construction. A microscopic imperfection can grow under strain. A weld that appears seamless in the air may behave differently in the cold, dark water below. Inside such a sphere, the environment must remain stable while the outside world attempts to crush it. The difference between the two creates an enormous imbalance. The deeper the descent, the greater the disparity becomes, and the more precise every part of the structure must be. Even with the best materials, the strongest alloys, and the most refined engineering, the ocean at the deepest points remains a challenge that cannot be taken lightly. Pressure also alters how materials behave over time. Metals that seem rigid may slowly deform after repeated dives. Bolts may tighten or loosen subtly. Seals may shift in ways invisible to the eye. The physics of the deep sea does not act only in moments of collapse. It works slowly and continuously, shaping the lifespan of any vessel that enters its domain. To imagine the effect is to imagine being surrounded by a world that gently, persistently presses inward from every direction. The pressure does not roar, it does not strike, it simply exists, steady and absolute. Everything beneath it must adapt, yield, or resist. When engineers design for these depths, they do so with quiet respect, knowing that the ocean will accept nothing less than perfection. And so vessels that descend into the trench are crafted with painstaking care. Every curve, every weld, every layer of material is chosen with the knowledge that 16,000 pounds on every inch is waiting below. The sphere becomes a symbol of this careful balance, shaped by physics, refined by necessity, and carried downward by the hope that it will hold. Around it, the water grows heavier still, surrounding the craft like a vast and ancient presence. The deeper it travels, the more the ocean reveals the quiet strength that has shaped its hidden world for millions of years. As the descent continues, the trench surrounds us with a darkness that feels almost ancient. Earlier chapters carried us from the world of shifting plates into the quiet weight of pressure, where matter bends and metal strains beneath forces gathered over miles of water. Now another transformation unfolds, one shaped not by weight or motion, but by the slow disappearance of light itself. It happens gently at first, almost unnoticed, then more swiftly as depth increases, like a soft curtain being drawn across the entire world. Sunlight begins its journey at the surface with brilliance. It dances across waves and filters downward in shimmering beams. But water is not an empty space. It absorbs, scatters, and weakens every color, reducing their strength with each passing meter. The deeper one travels, the more the ocean becomes a place sculpted by light's retreat. Red wavelengths vanish almost immediately. They fade within the first few dozen meters, swallowed by water that favors shorter wavelengths. Orange follows soon after, then yellow, then the greens that cling to visibility a little longer. By the time a traveler descends a few hundred meters, the only surviving color is blue, soft and faint, carried by wavelengths that slip more easily through the dense medium. This is why the upper ocean glows with that familiar blue hue, and why everything beneath it slowly shifts into twilight. But even this last color cannot endure the long journey into the trench. The water grows colder, denser, and darker. Suspended particles drift like tiny stars, each one scattering light into different directions. Step by step, meter by meter, the illumination narrows until it disappears entirely, leaving only blackness as deep as space. It is not the absence of beauty, but the presence of physics, shaped by the way light interacts with water that thickens as the weight of the ocean grows. In this vast darkness, explorers try to bring their own illumination. Modern LEDs shine with remarkable strength at the surface. They are engineered for clarity, brightness, and durability. Yet as they descend into the Hadal world, they meet the same rules that govern sunlight. Water absorbs their beams just as easily, swallowing their energy in silent layers. Even the most powerful LEDs, glowing with thousands of lumens, can only carve a narrow bubble of visibility around a submersible. The beam stretches outward for a few meters, maybe a handful more, then fades like breath on a cold window. It is not simply the distance that weakens the light. Pressure tightens the water, increasing its density and the number of molecules a photon must encounter. Each collision saps the light a little more. Particles suspended in the Hadal zones reflect beams unpredictably, creating flares and ghosts in the darkness. Small organisms drift by, scattering rays that were meant for the seafloor. Sediment, stirred by tiny currents, adds another layer of distortion. Light that might illuminate a wide scene in shallow water becomes a pale, trembling circle here, shrinking the world to the size of a small room. This limitation quietly transforms every attempt to film or photograph the trench. Cameras, no matter how advanced, depend entirely on the light available. In the deep sea, the available light is whatever the vessel can generate. With only a thin shell of brightness around them, cameras capture a world that appears closer, narrower, and more intimate than it truly is. The seafloor might stretch for hundreds of meters in either direction, but the camera sees only the patch directly in front of the lens. Any creature that swims even a body's length away moves into complete obscurity, swallowed not by distance but by a thickness of water that smothers illumination. This limitation gives deep-sea imagery its characteristic look. Scenes appear as softly lit islands surrounded by perfect black. Shadows fall sharply because there is no surrounding ambient glow to soften them. Colors shift into cooler tones as the camera relies heavily on the narrow wavelengths that can survive the journey through the water. Even high-resolution sensors cannot change this. They can only record what the limited light allows them to see. When engineers design cameras for trench exploration, they consider the way the ocean alters every photon. Sensors become more sensitive. Lenses gather as much light as possible. Software attempts to lift details from the dim footage. Yet none of these improvements can replace the fact that the ocean itself swallows most of the illumination before it ever reaches the camera's eye. Even a full array of lamps cannot push far into the distance. The surrounding blackness is not empty. It is a wall built from the water itself, shaped by absorption and scattering and the physics of extreme depth. Still, within this darkness, the faint cone of LED light becomes a kind of gentle guide. It reveals rocks and sediments that have lain unseen for ages, drifting creatures that pass gracefully through the beam, and the quiet texture of a world far removed from sunlight. The lack of widespread visibility does not diminish the landscape. It simply frames it differently, placing emphasis on the details close at hand, the small movements, and the subtle shapes carved by slow geological time. In this way, the deep ocean becomes both hidden and intimate. Each illuminated moment feels like a soft discovery, emerging from a darkness that has existed far longer than human curiosity. The light may reach only a short distance, but within that circle lies an entire world shaped by pressures and temperatures and ages uncounted. The camera, limited by physics, captures what it can. The rest remains quiet, untouched, and waiting in the stillness beyond the beam. As our journey continues downward, the ocean shifts from a place shaped by light into one defined entirely by its absence. In the earlier sections, we drifted through the last fading traces of sunlight, watched colors dissolve in the water, and felt the quiet narrowing of visibility. Now the descent carries us into a realm where even artificial brightness, no matter how powerful, cannot restore what has been lost. This is the threshold of photic darkness, a term that describes far more than darkness itself. It marks the depth where light no longer behaves as a guide, a language, or a presence. It becomes something that exists only in memory. Photic darkness begins slowly, like dusk settling across a landscape. Sunlight weakens, softens, and finally vanishes. But what replaces it is not simply night. Night on the surface still holds reflections, moonlight, stars, and the pale glow of distant horizons. In the ocean's deepest reaches, the darkness is complete, uninterrupted, and ancient. It is a kind of darkness that behaves like a physical presence, shaping every movement and influencing every decision. It surrounds a vessel gently, yet its reach is absolute. When explorers describe photic darkness, they speak of it as a boundary where human senses begin to lose their anchor. Without light, distances lose meaning, shapes blend into emptiness. The idea of direction becomes something felt rather than seen. Navigation, which depends so much on the ability to track movement against a visible world, becomes a delicate act. Instruments must take the place of eyes, guiding a vessel using math and memory rather than sight. In this realm, a submersible drifts through water that seems infinite. The familiar cues of orientation are gone. There is no up or down except for what the instruments tell the crew. The craft's beams push outward in narrow cones, illuminating only a few meters before dissolving into the black. Even within that small circle, shadows behave unpredictably. They stretch in strange ways, as if the water itself bends them. The boundary between illuminated space and surrounding darkness feels as sharp as the edge of a cliff. Navigating through this darkness requires constant attention. A gentle rise in the seafloor may appear suddenly, revealed only at the last moment by the thin halo of light. A wall of rock may emerge from nothing, its shape only partially visible before the craft glides past it. Without the ability to see more than a narrow slice of the world, movement becomes a slow and careful conversation between sensors and environment. Yet, the darkness alone does not make navigation difficult. The water itself, filled with drifting particles, creates illusions that deceive even the most experienced observers. Small flakes of sediment, lifted by faint currents, float through the beams of the submersible. Each particle catches the light briefly, then fades as it drifts back into the unseen. Some glimmer like distant stars, others streak across the frame like falling sparks. In moments, these movements create the impression of speed, even when the craft moves slowly. The eyes interpret forward motion where none exists, or mistake the drifting of particles for the sliding of the seafloor. These illusions can distort the sense of space. A cluster of particles passing close to the lens may look like a distant cloud. A ribbon of silt, stirred by the vessel's own thrusters, can appear as a flowing current or a rising slope. Even the reflection of particles bouncing off the craft's hull creates tiny flashes that echo across the darkness. To the camera, these reflections resemble shapes emerging from the void. For a viewer, they feel like brief sparks in a world otherwise defined by stillness. The slow drift of particles also alters depth perception. In the surface world, the brain calculates distance by comparing the size and clarity of objects within view. In the deep sea, these cues vanish. A small piece of sediment close to the camera may appear identical to a larger object farther away. Without light to soften or sharpen edges, the eye can no longer trust its instincts. Everything becomes equal in the dark. Everything seems to exist at the same distance, suspended in a space without clear boundaries. The seafloor itself can hide behind these illusions. When a submersible approaches the bottom, the particles stirred by its descent rise like a soft cloud. They shimmer gently in the beams, forming confusing patterns that obscure the true shape of the ground. The craft might believe it is still descending through open water when, in reality, the bottom lies only a few meters away. It is one reason why landing in the Hadal world requires such careful control. Darkness changes not only what can be seen, but how distance and motion are interpreted. Photic darkness turns the deep ocean into a place where perception must be rebuilt from the ground up. Every instrument becomes a substitute for sight. Every particle drifting past becomes part of a shifting tapestry that must be read with caution. Navigation becomes the art of trusting faint signals, gentle movements, and the subtle language of a world that existed long before light ever found its way into the universe. In this silence and shadow, the trench reveals itself in pieces, softly and slowly, giving just enough for explorers to understand its presence, while the rest remains hidden beyond the reach of even the brightest lamps. As we continue our quiet journey downward, the deep ocean reveals yet another of its hidden structures. It is not a cliff or a valley, nor a current or a creature. It is a boundary made not of stone or water, but of temperature. The ocean, though seemingly uniform from the surface, is layered like a slow and shifting tapestry. Warm waters rest above, cold waters pool below, and between them lies the thermocline, a vast and gentle wall where the world changes with surprising speed. At the surface, sunlight warms the upper layer of the sea. Waves mix this warmth through dozens of meters, sometimes hundreds, creating a region where temperatures remain relatively steady. But as one descends, a moment comes when the water cools sharply, as if one has stepped through an unseen doorway. The shift is not subtle. It is a plunge into cold that deepens quickly, each meter bringing a new chill. This zone of rapid temperature drop is the thermocline, a natural barrier that stretches across entire oceans. The thermocline moves and breathes with the seasons. In some places it rises, in others it sinks. But wherever it appears, it marks a transition between the world shaped by sunlight and the dark realm shaped by pressure and cold. It is the point where heat from above can no longer cling to the water, where the deep begins to reveal its true nature. For a submersible, crossing this layer is like drifting from one environment into another. Above the thermocline, the hull feels the gentle coolness of the midwater world. Below it, the hull meets cold so intense and persistent that even the strongest materials contract slightly under its influence. Temperature changes the density of water, which in turn alters how a vessel moves. A craft designed to glide smoothly through warmer layers may suddenly find itself less buoyant, responding sluggishly to adjustments that were effortless moments before. This shift in density can affect the ascent and descent of any deep-sea vehicle. The vessel may sink more quickly upon entering colder layers, then rise more slowly when returning to warmer ones. Engineers plan for this, but the ocean rarely offers perfect predictability. Small fluctuations in temperature create pockets of water with different densities, each one nudging the vessel subtly. These nudges accumulate, turning the descent into a long and careful negotiation with the surrounding environment. Some submersibles adjust automatically, using ballast systems and thrusters to maintain balance, but even the most advanced designs feel the influence of the thermocline. A momentary drift in buoyancy might cause the craft to tilt, or hover, or pause unexpectedly. Navigators learn to anticipate these effects, reading their instruments like a mariner reads the stars, knowing that the ocean offers guidance through patterns too subtle for the eye to see. Temperature also shapes the inner workings of the submersible. Electronics, though sheltered within pressure-resistant housings, remain sensitive to the cold. Batteries lose strength as temperatures fall. Their chemical reactions slow, reducing the energy they can deliver. A battery that performs well at the surface may offer only a fraction of its strength once the craft sinks beneath the thermocline. This decline is not sudden, but gradual. With each drop in temperature, electrons move less easily through their circuits. Power reserves that seemed full become thin, and systems that rely on constant energy begin to operate more cautiously. Lights may dim slightly, thrusters may lose a little of their push. Sensors that depend on delicate measurements might respond more slowly or with reduced clarity. Most deep-sea explorers compensate by using heaters or insulating layers within their equipment. These measures protect the electronics, keeping them warm enough to function. Yet heating requires energy, and energy is always limited on a deep dive. The colder the descent becomes, the more energy must be used simply to keep the craft alive. Every minute spent in the deep is a balance between science and survival, illumination and endurance. Even the simplest component behaves differently in the cold. Rubber seals stiffen, lubricants thicken, metal contracts. These small changes, while harmless on their own, can create challenges when combined with the immense pressure that waits below. Engineers must account for these transformations long before the vessel ever touches the water. Every material must be chosen for its ability to withstand a world where temperature and pressure work together, each one shaping the craft in quiet, persistent ways. The thermocline itself, though invisible, leaves a clear mark on the journey. Above it, the water carries faint traces of warmth. Below it, the cold settles like a blanket, woven from centuries of stillness. The boundary between these two realms is delicate, yet distinct. As a submersible passes through it, the sound of the hull shifts slightly, as if the cold tightens around the metal. Instruments register the drop. Lights seem to glow against a darker canvas. The ocean grows quieter, colder, and more immense. In this region, where temperatures fall so quickly, the ocean reminds us that depth is not defined by distance alone. It is shaped by layers, each with its own personality. The thermocline is one of these layers, a curtain separating the familiar world of light from the mysterious world below, guiding the vessel downward into the deep where cold and pressure join to create a landscape few eyes have seen. As we continue drifting downward, the cold deep begins to feel less like ordinary water and more like a world with its own quiet physics. In earlier chapters, we passed through the thermocline, where warmth surrendered suddenly to cold. Now we enter a realm where that cold shapes the very nature of the seawater itself, guiding how it moves, how it holds weight, and how it touches the machines that dare to enter. Down here, chemistry becomes part of the landscape. The seawater in these depths grows dense under the weight of the ocean above. Each layer presses gently on the one below it, tightening the arrangement of molecules until they sit closer than they ever do near the surface. This density does not shout its presence. It feels more like a soft heaviness, a quiet thickening of the world. A drop of water at the surface might drift freely, but a drop in the Hadal zone carries the memory of pressure within it. Temperature adds to this transformation. The cold that settles across the deep sea slows molecular motion until the water takes on a subtle viscosity, as though moving through it requires a little more patience. Salinity plays its part as well. Salt, dissolved over countless years, changes how water behaves under pressure. In the deep trenches, currents sweep older waters from far corners of the Pacific, carrying minerals gathered from distant shores and seafloors. These slow, ancient currents fill the trench with brine that is slightly saltier, slightly heavier, and slightly colder than the water above. Together, these small changes reshape the very medium through which any submersible must travel. With this altered chemistry, something as simple as buoyancy becomes beautifully complex. Near the surface, buoyancy calculations are straightforward. Engineers can predict how their vessel will rise or sink with precision, but as the craft enters deeper layers, the changing density of the water disrupts these expectations. Below the thermocline, the water becomes heavier with every meter, and the submersible may respond in ways that feel almost alive. A vessel that hovered gently at one depth might begin to sink unexpectedly when it drifts into slightly denser brine. Another might hesitate when rising, slowed by pockets of cold water that cling to its hull. Even slight variations in temperature can alter the water's density enough to shift the craft's behavior. A region only a few degrees colder becomes a pocket of heavier liquid that tugs gently downward. This means buoyancy must be managed with care in a slow and constant conversation between ballast, thrusters, and environment. The ocean below 6,000 meters does not offer uniformity. It offers layers that move like soft currents of glass, each with its own weight. For the explorers who design these vessels, this unpredictability becomes part of the challenge. They run calculations that account for density, salinity, and temperature profiles. Yet the ocean always keeps small mysteries within its depths: a rise in salinity from an underwater current, a shift in water mass brought by far wandering tides. These variations may alter the submersible's trim by only a fraction, but in the deep sea, a fraction can change how the craft drifts, how quickly it sinks, and how long it can hover near the seafloor. Deep sea chemistry also shapes the relationship between water and metal. The hull of a submersible, built to withstand immense pressure, encounters brine that behaves differently from the water near the surface. Cold water carries oxygen in lower amounts, but it remains rich in dissolved salts and minerals. These minerals interact with metal surfaces in quiet ways. Over time, even the strongest alloys feel the subtle sting of corrosion. The cold slows certain chemical reactions, yet pressure and salinity encourage others, creating a delicate balance that engineers must understand long before the craft enters the abyss. As the vessel travels deeper, its hull becomes cooler. The cold brine presses tightly against it, forming a thin film of water that behaves differently than the water farther away. This film may cling more stubbornly to the metal surface, altering how heat is transferred between the vessel and its surroundings. Electronic housings may cool unevenly, affecting how circuits behave. The same brine that feels calm from afar becomes a quiet sculptor when it meets the surface of the craft, testing its coatings, its seals, and even the texture of the metal itself. In certain conditions, trace minerals within the brine can concentrate on the hull, forming small deposits that gather grain by grain. These deposits, while delicate, change how the water flows around the craft. Roughness increases drag. Smooth curves become subtly altered by microscopic layers of salt. Over many dives, these tiny changes can affect how the submersible moves, how much energy it consumes, and how long it can remain at depth. Cold brine also influences lubricants and moving parts. Joints and hinges stiffen slightly. Bearings respond more slowly. Materials that behaved predictably at the surface reveal new personalities under the combined influence of cold and pressure. Engineers must test their designs in controlled environments, cooling and compressing water until it resembles the deep ocean. Yet the real trench still offers surprises that no laboratory can fully recreate. As we picture the vessel drifting through these layers, we can imagine the water touching every surface with honesty. It presses, cools, and cradles the craft, while its chemistry transforms each moment of the descent. It is not hostile. It is simply different, a world shaped by weight, cold, and time. A world where even water carries secrets, whispering them through changes in density and salt and the soft persistence of deep ocean chemistry. As our journey settles deeper into the trench, the ocean reveals another truth about its hidden world. The quiet darkness, the cold brine, and the immense weight of the water above might suggest a stillness that never shifts. But the seafloor beneath this calm surface is far from motionless. It rests in a place shaped by the slow collision of tectonic plates, a place where the earth continues to move quietly, tirelessly, and sometimes suddenly. Down here, the landscape is alive in a way that does not echo with sound, but ripples through stone and sediment in soft, persistent tremors. The very trench itself is born from motion. Earlier chapters carried us through the story of one plate bending beneath another, creating a deep scar across the ocean floor. That motion never stops. It continues inch by inch, year by year, as the Pacific plate slides beneath the Philippine plate. This slow descent releases subtle energy into the surrounding rock. Much of it is gentle, almost unnoticeable, yet it adds up to a world where microquakes are a steady part of the environment. Microquakes are tiny earthquakes, too small to feel on the surface and too brief to disturb the water directly. But along the trench walls and floor, they reshape the landscape grain by grain. These small tremors loosen sediments that cling to steep slopes. They shift buried stones into new positions. They create faint vibrations that travel quietly through the deep crust. A submersible drifting nearby will not sense these tremors through movement. Instead, they become part of the unseen environment, a whisper of geological change passing through the rocks below. Over time, these tremors release sediments that have rested patiently along the trench walls. The particles do not fall in dramatic slides at first. Instead, they drift downward in billowing veils, forming slow-moving clouds that travel across the seafloor. The darkness of the trench hides their true scale. Within the reach of a submersible's lights, they appear as gentle flurries of silt, each particle settling through the still water with unhurried grace. But beyond the narrow glow of those lamps, these clouds can stretch for great distances, carried by faint currents that wander along the trench floor. Sediment in the Hadal world behaves differently than sediment near the surface. Without sunlight, without strong currents, without plant life to cling to it, the silt remains fine and easily stirred. Once lifted, it may stay suspended for hours or days. A single disturbance on a distant slope can release a cloud that travels far through the deep, gently obscuring everything in its path. Cameras and sensors see only a soft haze where sharp features once stood. Rocks blur into silhouettes. The ground becomes a watercolor, impossible to map until the silt finally settles once more. These drifting clouds create challenges for explorers. A probe lowered into the trench may find itself surrounded by a storm of fine particles, unable to see more than a few inches in any direction. Instruments that depend on accurate readings struggle as silt interferes with sensors. Lights reflect off the suspended grains, creating shimmering illusions that distort the shapes of the seafloor. Even after the cloud passes, the landscape may look different, the sediment having settled in new patterns shaped by gravity and time. The quiet motion of microquakes can also build toward larger changes. Along the steep walls of the trench, thick layers of loose sediment accumulate over centuries. These deposits cling to the slopes like snow on a mountainside. When enough stress builds beneath them, or when a cluster of microquakes ripples through the region, the sediments may lose their hold and begin to slide. An underwater landslide in the Hadal zone does not resemble the quick movements familiar on land. It begins with a slow, heavy fall, as though the ocean is exhaling a deep breath. Clay, sand, and gravel break free from the slope and move downward in a thick, rolling current. This movement stirs the deep water into a dense surge, sweeping across the floor of the trench. The slide may travel far, reshaping sections of the seafloor, covering old features and creating new ones. Such events can bury probes and instruments left on the bottom. A device resting peacefully on the seafloor may find itself swallowed by a layer of sediment many meters thick. Even large objects can disappear beneath these shifting layers, hidden beneath sediments that settle quietly over them. Recovery becomes almost impossible in a world where navigation is limited and where the seafloor changes without warning. Engineers who send equipment into the trench know that the landscape itself is never fixed. A map created one year may be slightly inaccurate the next. What was once a flat plain may become a ripple of new deposits. A small ridge may vanish beneath a fresh layer of silt. The continual motion of the plates ensures that the trench remains a place in transition, shaped by forces that act slowly most of the time, and suddenly when the earth releases the tension it has carried. Yet, this movement is part of the deep sea's ancient rhythm. The trench has shifted for millions of years, its walls rising and falling in response to the slow dance of the Earth's crust. Each quake, each cloud of silt, each landslide adds a new layer to the story of the ocean floor. Far from being a static place, the Hadal region is a landscape that breathes, changes, and renews itself in its own patient way. In this quiet world beneath the waves, the ground itself moves with the calm persistence of deep time, shaping a realm that remains mysterious not because it is still, but because it is always becoming something new. As our quiet descent continues, the darkness around us deepens into something almost ancient. Light has vanished, leaving the world shaped by weight, cold, and slow geological motion. But while the deep sea silences the eye, it awakens the ear in unexpected ways. Down here, sound becomes the language of the water. It travels farther than light ever could, weaving through the trenches with a patience shaped by distance and pressure. The abyss may appear empty, yet it hums with voices that span entire oceans. Sound moves differently in water than it does in air. In air, it fades quickly, swallowed by wind and space. In the deep ocean, sound travels faster and farther, carried by the dense and cold water with remarkable clarity. At certain depths, narrow bands of temperature and pressure allow sound to travel for thousands of kilometers without losing much strength. This natural pathway is sometimes called a sound channel, a gentle corridor that guides vibrations across the planet. One of the most haunting travelers through this channel is the call of whales. Their voices, deep and melodic, can pass from one side of the ocean to the other. A blue whale singing near the equator may be heard near the poles by hydrophones resting in silence. The sound is low and powerful, shaped by the whale's immense body and carried through the water with effortless grace. These calls help whales find mates, trace migration routes, and sense distant landscapes. To a listening device in the trench, a whale many hundreds of kilometers away may sound as though it is nearby, its voice softened only slightly by the journey. Alongside the whales, the earth itself speaks. Tectonic rumbles echo along the trench walls, quiet reminders of the slow motion of the plates beneath us. These rumbles are not violent in the way earthquakes feel on land. Instead, they present themselves as rolling vibrations, long and low, as though the earth is shifting in its sleep. Hydrophones anchored near the trench floor detect these signals with astonishing clarity. Some arrive as gentle murmurs, others as deeper tremors that travel along the rocky slopes before fading into the stillness. These tectonic sounds reveal a world of constant motion. They capture the shifting of stone, the settling of sediment, and the soft cracking of old crust as it moves beneath younger layers. To scientists listening from the surface, the deep ocean becomes a continuous, slow moving symphony. Each tremor tells a story of pressure, release, and the quiet sculpting of the seafloor. Yet, not all the sounds heard in the abyss have explanations. Over the past decades, hydrophones placed near trenches have recorded mysterious low frequency noises. Some repeat across seasons. Others appear only once, then fade forever. These unidentified sounds often linger at frequencies difficult for the human ear to notice, but they reveal themselves as deep vibrations on audio instruments. Their origins remain uncertain. Some may be generated by distant storms, pounding waves, or powerful currents. Others may arise from geological activity, the movement of magma, or the shifting of stone deep within the crust. There is also the possibility that some of these sounds come from life forms we have yet to study. The trench holds many mysteries, and in places where even cameras struggle to see, sound becomes the first and sometimes only clue to what moves in the dark. These unexplained noises often carry a rhythm unlike anything created by wind or water. They drift softly through the deep, filling the abyss with distant echoes that spark curiosity and wonder. But sound, for all its reach and clarity, also creates challenges for navigation. A vessel in the trench cannot rely on audio cues to determine distance or direction. Sound reflects unpredictably off the steep walls, bending around ridges and scattering into the deep. A single noise may reach the submersible from multiple angles at once, making it nearly impossible to tell where the source lies. A whale call might seem close even when the whale is far beyond the horizon. A tectonic rumble might echo in strange patterns, arriving from above, below, and both sides. The density of the water, along with the shifting layers of temperature and pressure, bends sound waves as they travel. A signal sent from the submersible may curve downward unexpectedly or drift upward into warmer layers. Instruments must work hard to interpret these distortions. Even with advanced algorithms, the reflections that bounce along the walls and floor of the trench confuse the readings. A simple measurement of distance can become tangled in echoes that carry false information. For this reason, audio navigation in the deep sea remains nearly impossible without other guiding tools. Despite these challenges, the soundscape of the abyss remains one of its most captivating qualities. It is a world defined by vibrations, murmurs, and long-distance whispers. The trench, though hidden from sunlight, exists within a tapestry of sounds shaped by living giants, moving plates, and phenomena scientists are still learning to understand. Down here, every movement, large or small, sends energy through the water. The darkness may hold the world in silence for the eye, but for the ear, it reveals a place alive with subtle voices. In this quiet, cold landscape, sound becomes the storyteller. It carries the echoes of whales traveling across entire oceans, the slow rumbles of ancient earth shifting beneath the crust, and the mysterious tones that drift through the trenches, hinting softly at what lies beyond sight. As our journey continues deeper into the silent world below, it becomes clear that the ocean is not simply a place of unusual landscapes and shifting chemistry. It is also a realm that shapes the very boundaries of life. Machines can descend into these depths with great effort and delicate engineering, but the human body, remarkable in its own way, is shaped for a different world entirely. Long before the pressures of the trench become a threat to metal and electronics, they would overwhelm the soft structures that keep a person alive. Near the surface, the water presses on the body with a weight we hardly notice. The lungs expand easily, blood flows without strain, and the heart beats with its familiar rhythm. Divers can explore the upper world of coral reefs and sunlit slopes with only simple equipment. But every 10 meters of depth adds a full atmosphere of pressure, and the human body has limits shaped by evolution at sea level. These limits appear quickly, long before the glowing blue fades into darkness. A few dozen meters down, the pressure begins to compress the chest. The lungs must work harder to inflate, and the gases inside them grow dense. Breathing becomes a careful balance of physics and biology. Divers switch to specialized mixtures, reducing the amount of nitrogen they inhale to avoid the slow poison of gas absorption under pressure. Yet, even these measures only extend safety a little deeper. At greater depths, the gases in the bloodstream reach concentrations the body cannot handle. Nitrogen begins to interfere with the nervous system, creating a dreamlike fog that can distort judgment. Oxygen, normally the giver of life, becomes toxic when pressed into the body at high pressure. This delicate chemistry forms an invisible boundary in the ocean. The deeper one goes, the more the gases inside the lungs begin to behave in unfamiliar ways. Molecules push into tissues, dissolving into the blood in amounts that overwhelm the natural balance. Muscles, built for motion, become sluggish under the weight. The fine membranes in the lungs, responsible for exchanging gases, stretch to their limits. Past a certain point, the human chest cannot expand at all. Breathing becomes impossible without support. Technology can help bridge the divide for a while. Pressurized diving suits allow explorers to reach depths once thought unattainable. These suits hold an internal pressure close to the surface, protecting the body from the crushing weight outside. But even these marvels have limits. They work like small vessels wrapped around a person, and every increase in depth demands thicker walls and stronger joints. Soon the suit becomes as heavy as a machine, unable to move with the grace and precision that a diver needs to navigate the underwater world. There is also the problem of flexibility. A human cannot be encased in rigid metal without losing the ability to bend, turn, or reach. Engineers have tried to solve this challenge by designing suits with articulated joints, but these joints must resist immense pressure. Each one becomes a potential point of failure. At great depth, the strength required to keep the suit intact makes movement stiff and tiring. A suit that could withstand the weight of the trench would be so rigid that a person inside it could barely move at all. Even if such a suit existed, another barrier remains. The body relies on pressure differences to function. Blood moves through vessels because the heart pushes it. Tissues rely on gradients to exchange nutrients. If the pressure outside the suit becomes extreme, while the inside remains close to normal, the suit must carry the full force of that difference. Any flaw, any weakness, any disruption in the system would place the person inside at immediate risk. The boundary between safety and danger becomes razor thin. Because of these limits, humans can dive only a few hundred meters unaided and only slightly deeper with advanced equipment. Beyond that point, the physics of the ocean and the biology of the body part ways. The deep becomes a place meant for machines, built from alloys and composites that do not breathe or pulse. It is a world where soft tissues cannot survive, where the delicate machinery of lungs and blood and nerves would fail long before the trench revealed its hidden floor. This does not make the deep ocean hostile, only different. The human body is beautifully adapted to life in the air, where pressure remains steady and the lungs can expand freely. The ocean, with its growing weight and shifting chemistry, asks for a different kind of resilience. In its upper layers, humans can swim, explore, and study. But as the world darkens and the pressure grows, biology must yield to engineering. In this way, the trench becomes a reminder of the limits of flesh, shaped by millions of years in a gentle atmosphere. It is a place that welcomes machines built for the deep, and a place where human presence must remain distant, observing quietly from within protective shells or from far above on the surface. Through these limitations, the ocean keeps a part of itself hidden, waiting in the cold silence below. As our quiet journey sinks deeper into the abyss, the world outside becomes a realm shaped entirely by pressure, darkness, and cold. We have followed the limits of the human body, watched how lungs and tissues surrender long before the trench reveals its floor. Now we turn to the machines built to go where we cannot. Submarines, with their smooth shells and steady lights, seem resilient from the surface. Yet in the Hadal world, even the strongest vessels begin to reveal their limits. The deep ocean tests them gently at first, then relentlessly, until the craft must either yield or turn back. Pressure, patient and absolute, becomes the first sculptor of failure. The hull of any deep-sea vessel carries the weight of everything above it. Each meter adds a little more force, and although the vessel is designed to resist, the ocean presses in with perfect consistency. This is not a sudden attack. It is a slow gathering of stress, spreading across every curve and seam of the craft. Engineers spend years shaping these hulls into forms that distribute pressure evenly. Spheres and cylinders become favored shapes, their smooth surfaces guiding the force across the metal without concentrating it in any one place. But even with careful design, stress accumulates. The metal bends by microscopic amounts, too small to see with the eye, yet meaningful in the physics of the deep. Each dive presses the hull into a slightly different shape. When the vessel rises, the metal relaxes again. This cycle repeats with every descent, like a slow breathing motion that places wear on the material. Over time, tiny stretches and compressions begin to alter the hull's structure. The metal weakens in places where stress gathers more easily, often in curves that are not perfectly smooth or in sections joined by welds. Each change is subtle, yet together they form the long story of strain. Within this story, microfractures appear. These fractures are invisible cracks within the metal, smaller than the width of a strand of hair. They form where the material has been stressed again and again, where pressure has found slight imperfections that existed even before the vessel touched water. At the surface, such fractures pose no danger, but at depth, they become points where the hull is more vulnerable. When a vessel descends repeatedly, these fractures can grow, opening by the smallest degree under enormous force. They do not announce themselves with warning. They simply widen slowly, guided by pressure that never rests. A hull that once felt unbreakable begins to reveal its fatigue, not dramatically, but in silent internal shifts. Engineers scan for these fractures carefully, using ultrasound to search for the faintest traces. They repair what they can, yet the deep always leaves its mark, and every vessel carries with it the memory of every dive. Beyond the hull, other parts of the submarine face their own challenges. Hatches, seals, and joints, though designed with precision, must withstand pressure that tries constantly to push into the craft. A hatch may seem secure on land, locked into position with metal bolts and sturdy hinges. But at several thousand meters below the surface, each bolt bears a weight far greater than its size suggests. The hinges feel strain they never encounter in shallow water. The seal between hatch and frame is pressed together with enormous force, yet a tiny imperfection, a grain of sediment, or a shift in temperature can compromise it. Seals are especially vulnerable to the deep. They must remain flexible to work properly, but the cold stiffens them. The pressure squeezes them tightly, pressing the material into shapes it was never meant to hold. Over time, seals take on the memory of these shapes. They warp slightly, lose elasticity, and become less able to form perfect barriers. A seal that fails will not leak slowly. At depth, water does not trickle in. It arrives instantly, filling any gap with the full force of the ocean. A single failure can overwhelm the interior of the vessel in a moment. Joints face similar challenges. They connect sections of the submarine together, creating places where the hull must withstand pressure despite slight differences in shape and material. These joints experience stress differently than the smooth surfaces around them. Even the most carefully designed connection can become a weak point as pressure pushes on it from every direction. Metal plates may shift by tiny amounts. Bolts may loosen or tighten under the influence of temperature and pressure cycles. Lubricants inside the joints become thick and sluggish, reducing the joint's ability to move or hold its intended shape. The deeper a vessel travels, the more the ocean tests each of these parts. None fail immediately, yet all move slowly toward their limits. Some vessels retreat long before reaching the trench floor, knowing that another dive might push the structure beyond what it was meant to endure. Others try for the bottom, and while many succeed, each descent leaves subtle signs of fatigue. Engineers read these signs and decide whether the vessel can continue its journeys or whether it has reached the end of its safe life. In this quiet, immense world, submarines are reminders of how far human ingenuity can go and how much the deep sea chooses to allow. The ocean does not resist them with sudden force. It simply surrounds them with steady weight, cold, and time. Every part of the vessel must stand against these elements. And in the trench, even the strongest craft must acknowledge that they, too, are shaped by the deep, tested gently at first, then thoroughly, until the journey must pause once more at the edge of the unseen. As our quiet exploration moves deeper into the history of the trench, it becomes clear that the machines we send into the abyss are not only feats of engineering, but chapters in a long story of human curiosity. Long before modern submersibles descended toward the Hadal world with complex electronics and titanium shells, the earliest pioneers attempted to solve the problem of depth using the simplest and most elegant idea they had. They built a sphere. The bathysphere, created in the early 20th century, looked small and plain on the outside, yet it represented a profound leap in exploration. It was a hollow steel ball, thick-walled and heavy, just large enough for two people to sit inside with barely any space to move. The sphere hung from a cable attached to a ship at the surface. When lowered, it would sink slowly into the deep, carrying its passengers into a world no human had ever seen. It had no engine, no thrusters, no fins or propellers. It relied entirely on gravity to descend and on the cable to return to the surface. Inside the bathysphere, there were only a few small windows made of thick, fused quartz, each one painstakingly shaped to withstand the growing pressure. The explorers peered through these tiny portals as the light faded and the water around them shifted from blue to black. Without the lights of modern equipment, their view of the deep was limited to whatever drifted close enough to be illuminated by the simple lamps attached to the craft. Yet even this limited view was enough to transform the world's understanding of the ocean. For the first time, people gazed directly into the deep waters that had remained unseen for millions of years. The bathysphere solved one of the earliest challenges of deep exploration. It created a space strong enough to protect human life from pressures that would crush a body in an instant. The sphere shape, which distributes force evenly across its surface, proved to be the key. Even with the technology of that era, engineers understood the value of symmetry and strength. The bathysphere showed that a sealed, rigid chamber could survive depths far beyond what divers could reach. It offered a glimpse of a future where the deep ocean, once believed completely out of reach, could be studied with patience and persistence. But the bathysphere also revealed the limitations that would shape decades of exploration. Its cable was both its lifeline and its greatest vulnerability. Any weakness in the cable could have trapped the explorers at depth or dropped them beyond recovery. Steel wires strained under the weight of the craft, swayed slightly in currents, and endured the constant tension of movement on the surface ship. Engineers could not control where the bathysphere moved once it entered the water. It drifted with the ocean, unable to adjust its course or steady itself against the shifting currents. Inside the sphere, the explorers faced challenges that were not mechanical but human. The air grew warm and humid as they breathed, and there was no way to open a hatch to cool the interior. Moisture collected on the walls, and the small space amplified every sound, making the deep journey feel even quieter and more isolating. There was no ability to maneuver or steer. If the bathysphere rotated even slightly, the windows might point toward empty darkness for the entire dive. Despite these challenges, the bathysphere opened a doorway. It allowed researchers to record the existence of deep-sea creatures that had only been guessed at before. The soft glow of its lamps revealed animals with luminous bodies, drifting shapes, and delicate forms built to survive in the dark. It showed that life existed far deeper than many scientists believed possible. With each descent, the explorers wrote new chapters in the story of the ocean, even as they knew that this simple sphere could only take them so far. As time passed, newer vessels appeared. Engineers built submersibles that no longer depended on cables. These crafts used ballast systems, propellers, and batteries to travel through the deep with greater control. Each generation improved on the last, solving problems the bathysphere could never overcome. Modern submersibles can glide through the water, adjust their position, and illuminate the world around them with bright lamps. They carry sensors that measure pressure, temperature, and chemical composition. They bring back samples from the seafloor and record images with clarity the early explorers could not have imagined. Yet even with all this progress, some challenges remain unchanged. The pressure still grows with every meter. The cold still tightens metal and slows electronics. The deep still hides itself behind layers of darkness and drifting silt. The engineering miracles of today build upon the humble foundation laid by the bathysphere, but they face the same ancient ocean that tested those first fragile dives. The bathysphere was not perfect. It could not steer, could not linger safely near the seafloor, and could not explore freely. But it was enough. It carried human curiosity into a world that had waited in silence since long before people existed. In doing so, it became the beginning of everything that followed, a small steel sphere suspended in the deep, opening the door to an entire universe beneath the waves. As our quiet journey drifts onward, the story of exploration shifts once more from the early steel spheres of the past to the intricate machines that now carry human curiosity into the deep. These robots, shaped by decades of patient engineering, move through the water with a grace that humans themselves cannot achieve. Yet even they find the trench to be a world of challenges, where cold, pressure, and shifting currents test every design. It is here, in the silent Hadal depths, that deep-sea robotics reveals both its brilliance and its limits. There are two main kinds of robotic explorers that descend into these waters. Some remain tethered to the surface by a cable, guided from above like a delicate instrument lowered into another world. Others move untethered, free to glide through the dark as independent travelers. Each solves certain problems and faces others that grow sharper with depth. Tethered robots, often called remotely operated vehicles, carry a long umbilical cable that stretches upward to the ship. Through this cable, the robot receives power, instructions, and a steady flow of data. The tether becomes its lifeline, allowing the crew above to see through its cameras, steer its movements, and guide its arms as it gathers samples or inspects the seafloor. In shallower waters, this connection works beautifully, giving the operators on the surface a sense of presence in the deep. But the trench is an entirely different environment. Here, the tether must extend for many kilometers, through layers of shifting currents and pressures that change the nature of the water itself. As the robot descends, the cable drifts in the water like a long ribbon. Currents nudge it from side to side, creating gentle waves along its length. The weight of the cable increases with depth until it becomes a burden that strains both the robot below and the winch above. Even with buoyant sections placed along its length, the tether can sag under its own mass. When the currents pull strongly enough, the drag on the cable becomes significant, tugging at the robot with a force that makes fine movements difficult. The operator may try to guide the craft toward a particular ridge or trench, only to find the tether holding it back or pushing it sideways. This strain becomes most dangerous when the cable encounters unexpected loads. A shift in current, a sudden drop of the robot, or the cable's own weight settling into a curve can create tension strong enough to damage it. At the surface, the cable may move slightly with each roll of the ship. Down below, those movements translate into tightening or loosening across thousands of meters. The deep sea does not allow weaknesses in materials. A tiny flaw in the cable's outer layer can grow under the weight. A single section rubbing against a rock wall can fray over time. In rare cases, a sudden surge in tension can snap the tether outright, sending the robot drifting into the darkness with no way home. This risk is one reason untethered robots were created. These autonomous vehicles move freely through the water, unburdened by cables. They carry their own batteries, lights, computers, and instruments, making them self-contained explorers. They glide gently along the seafloor, recording images and measurements as they travel. Their independence allows them to reach places tethered robots cannot, weaving through narrow canyons, drifting above steep drops, and settling near delicate features without the drag of a long cable behind them. But freedom comes with its own limits. Without a cable to supply power, these robots depend entirely on their onboard batteries, which weaken steadily in the cold waters of the Hadal world. Buoyancy becomes another quiet challenge. Water in the trench grows denser with depth, and even small changes in density can affect how a robot floats. If the robot becomes even slightly heavier, it may sink more quickly than expected. If it becomes slightly lighter, it may drift upward, fighting the pull of gravity. Engineers design these machines with careful balances of foam, ballast, and structure, but the deep sea does not remain constant. A robot traveling through layers of water with different temperatures and salinities may experience shifts that complicate its motion. Some vehicles compensate with pumps that move water in and out of internal chambers, but these systems must withstand immense pressures and remain reliable through long dives. Thrusters, which allow robots to maneuver, also lose efficiency in the cold, dense water. Each blade must push against a medium thicker than the water near the surface, and each motor must work harder to achieve the same motion. As pressure rises, small gaps in machinery tighten, lubricants thicken, electrical components cool and slow. The robot may still be able to move, but its movements become gentler, more deliberate, shaped by the physics of the deep. A thruster that can turn the vehicle with ease in shallow water may struggle to overcome the drag of the tether or the weight of the cold water pressing against its frame. Yet, despite all these challenges, deep sea robots continue to reveal worlds once hidden entirely from human knowledge. They glide through canyons never seen by light, rest gently on slopes untouched for millions of years, and carry back fragments of the unknown. Their work is patient and precise, shaped by the quiet rhythms of the ocean that surrounds them. And though they face the limits of engineering and the weight of the world above, each dive brings us closer to understanding the deep, one careful movement at a time. As our quiet journey deepens, the story of exploration shifts once again, this time into the invisible lifeblood that keeps every machine alive. Light has faded, pressure has built, cold and chemistry have reshaped the water around us. Now we reach a realm where even energy behaves differently. In the Hadal deep, nothing comes easily, not even the simple act of keeping a machine awake. A submersible that drifts down the trench must carry its own source of power. It cannot breathe electricity from a surface ship as tethered robots do, because long cables become heavy burdens in such depths. Untethered vehicles rely on batteries, sealed behind thick walls to protect them from the enormous weight outside. Yet pressure does not simply squeeze the hull, it also changes how the components inside perform. Batteries that work smoothly in a warm laboratory begin to slow as they sink into the cold and the dark. Every battery is a quiet chemical conversation. Ions move through a liquid or solid medium. Electrons travel through circuits, and energy flows steadily to whatever systems need it. But in the deep sea, temperature falls until chemical reactions grow sluggish. The ions move more slowly, storing and releasing energy with less efficiency. A battery that offered many hours of power at the surface may give only a fraction of that time once the water temperature drops near freezing. The cold seeps into the structure of the cells, thickening electrolytes and stretching the time it takes for charge to move. Pressure adds another layer of challenge. Even inside the protective hull, slight flexing of materials can affect how battery packs sit, how wires align, and how cells maintain their internal structure. Engineers must build them with extra cushioning, extra insulation, and extra layers of protection that take up space and weight. Each added step keeps the battery safe, but reduces how much power can be stored in the small interior of a deep-sea vessel. The result is a world where energy must be rationed with care. Many people imagine nuclear power as a solution, a tiny generator glowing at the heart of a submarine, providing long-lasting energy that never fades. Large naval submarines do use nuclear reactors, after all, but the craft used for deep-sea research are very different machines. A nuclear reactor needs space for shielding, space for cooling systems, and systems to handle heat. It creates continuous warmth, which must be managed gently to avoid harming electronics. A small submersible cannot support such equipment. Its hull would need to be far larger, heavier, and more complex, making it impossible to descend into the trench. The pressure alone would crush the reactor chamber unless it was built extraordinarily thick, and such thickness would add more weight than the craft could ever lift. There is also the question of safety. A nuclear system that fails in the deep would leave behind materials that could linger in the ocean for centuries. Even the smallest risk is too great for such a fragile environment. For these reasons, deep-sea vehicles rely on batteries, not reactors, and must work within the limits that batteries impose. These limits shape every moment of a dive. Thrusters, the small propellers that guide the craft through the water, consume the most power. In the cold, dense water of the trench, each thrust requires more energy than it would near the surface. The blades must push against water that resists them more strongly, and the motors must work harder to turn. A simple turn or ascent may drain more energy than expected, forcing pilots and engineers to plan every movement with care. Thruster efficiency becomes a delicate balance of speed and survival. Move too quickly, and the craft burns precious power. Move too slowly, and currents may nudge it off course, requiring more corrections and more energy in the long run. Engineers choose thruster designs that sacrifice speed for endurance, allowing the vehicle to drift gently rather than fight the water aggressively. In the deep sea, strength matters less than patience. Lights, cameras, heaters, sensors, and communication systems also share the same limited battery. Each of them draws its own small stream of energy. Even the internal heaters that protect electronic components from freezing must be timed and monitored. If they run constantly, the battery fades too quickly. If they run too sparingly, the electronics cool and slow. Because of these limits, a dive into the trench often becomes a quiet negotiation. The vehicle measures its remaining power, compares it to the tasks ahead, and gently adjusts its course to make sure it can return. Every moment of illumination, every meter traveled, and every instrument activated is weighed against the energy required to rise back to the surface. The deepest parts of the ocean ask explorers not only to withstand the pressure and darkness, but to manage their energy with calm precision. In this distant world, at the bottom of the sea, power becomes a kind of soft heartbeat. It pulses through wires, warms circuits, and turns small propellers that guide the vessel across landscapes untouched for ages. The battery glows quietly within the cold, carrying the hope of discovery in every watt. And with each careful movement, the submersible honors the balance between ambition and endurance, drifting gently through a realm where energy is as precious as life itself. As our descent into the abyss continues, the silence around us becomes more than the absence of light or the vast stillness of the trench. It becomes the silence of communication itself, a gentle reminder that the deep sea obeys laws far different from the ones that guide our everyday world. Machines may endure pressure, lights may glow against the dark, and sensors may whisper their readings into memory, but the ability to speak across distance begins to fade long before the trench reveals its floor. In the familiar world above the waves, communication travels effortlessly through the air. Radio towers flicker with invisible energy. Satellites send signals across continents. Voices, data, and images pass freely between devices. But radio waves, for all their usefulness on land, meet their limit when they touch the ocean. Water absorbs them with surprising efficiency. Even shallow depths swallow their energy. The deeper one goes, the more absolute this silence becomes. Radio waves struggle in water because their frequency, so well suited to moving through the air, is quickly dampened by the dense medium. A few meters below the surface, the signal weakens. A few dozen meters later, it fades almost entirely. By the time a vehicle has descended even a small fraction of the trench, radio communication is impossible. No message can pass upward. No guidance can reach downward. The ocean, ancient and vast, protects its depths with a quiet barrier that technology cannot overcome. Without radio, deep sea explorers turn to sound, the same medium that carries whale songs across entire oceans. Sound moves faster and farther through water than it ever could through the air. Acoustic communication, built from pulses of carefully shaped vibrations, becomes the only remaining thread between the surface and the vehicle below. Yet this thread is fragile. It carries only simple messages and loses strength with distance. Acoustic signals must travel through layers of water that are ever changing in temperature, salinity, and movement. As these signals descend or rise, they bend gently, following curves shaped by the deep's shifting chemistry. Along the way, they scatter off particles, rocks, and pockets of cold. Each collision blurs the message a little more. A command that left the surface as a crisp instruction may reach the submersible as something softer, the edges of the message rounded away by the journey. This softness places limits on what can be sent. Complex data streams become scrambled. Detailed information becomes unreliable. Engineers must simplify their messages so they survive the long travel through the water. Words become pulses. Pulses become coded rhythms. Even with careful design, transmission errors remain common, especially in regions where trenches narrow and walls rise sharply on either side. Sound bounces unpredictably within these steep corridors, creating echoes that confuse the intended message. A single instruction may return to the surface multiple times, each echo overlapping the next, blurring the meaning further. The time it takes for sound to travel also creates practical challenges. In air, communication feels instant. On land, a device responds the moment a button is pressed. But in the deep sea, latency becomes its own kind of tide. A signal sent downward must travel through several kilometers of water before it reaches the vehicle. The vehicle then interprets the message, carries out the instruction, and sends a response back upward. By the time the surface receives the reply, several seconds have passed. In those seconds, currents may have nudged the vehicle. Sediment may have drifted into view. A small shift in the thrusters may have moved the craft unexpectedly. This delay makes precise control nearly impossible. Pilots operating from the surface cannot guide the submersible with the same immediacy they use for shallow water dives. They must anticipate movements instead of reacting to them. Every adjustment becomes a prediction. Every course correction becomes an act of trust in the machine and the environment. If a robot approaches a delicate formation or a steep wall, the pilot must hope the delayed response will not place it in harm's way. The deep sea becomes a place where caution replaces agility and where patience replaces speed. Even the simplest tasks can be complicated by these delays. A robot collecting a sample must align itself with great care. A pilot sends a command to move, then waits. The robot moves. The pilot waits again to see the result. Each tiny step forward stretches into a slow and deliberate dance. The deep rewards this slowness, offering safety through gentleness, yet it also restricts how much can be done in a single dive. Some explorers rely on fully autonomous vehicles to overcome this barrier. These robots do not wait for commands. They follow pre-written instructions stored within their systems, making decisions based on onboard sensors. Autonomy removes the need for constant communication, but it also means the craft must operate without guidance if unexpected changes occur. A cloud of drifting silt, a shifting current, or a rockfall along the trench wall might alter the landscape, and the robot must decide its own path forward. In this way, communication becomes less about speaking across distance and more about preparing for silence. The deep does not welcome real-time dialogue. It offers only faint whispers carried through water, softened by pressure and distance. Explorers must learn to design, plan, and act within this quiet world, trusting their machines to navigate the unknown without constant connection. And so, As we move deeper into the abyss, communication itself becomes part of the landscape, shaped by the same forces that carve the trench. It fades gently, like light before it, leaving behind a realm where only patience, preparation, and quiet confidence can bridge the vast silence between surface and sea. As we drift deeper into this silent world, we begin to understand that the ocean floor is not a fixed landscape. It is a place shaped by slow motion, soft shadows, and tiny particles that float with endless patience. Down here, even the smallest movement can stir the stillness, releasing a gentle storm that lingers far longer than any breeze or tide at the surface. These are silt storms, the deep sea's own quiet blizzards, built not of snow but of finely crushed fragments left behind by ancient geology. The seafloor of the trench is covered with sediments so soft that they resemble powder. These grains come from many places. Some fall from the upper ocean, drifting for months before settling in the calm darkness. Others come from the slow erosion of rock along the trench walls, broken apart by microquakes or landslides. Over time, these grains pile into thick layers that stretch across the narrow floor like a pale, weightless blanket. Unlike snow on land, which settles quickly after a single gust, deep sea sediment remains suspended when disturbed. The water is so still, so cold, and so dense that once a particle is lifted, it may take hours or even days for it to fall back to the ground. The slightest motion can send these grains swirling upward. A submersible's thruster, a robotic arm brushing the bottom, even the gentle settling of the vessel itself. All these movements create long, drifting clouds that expand slowly into the surrounding water. When a silt storm begins, it transforms the landscape instantly. Visibility, already narrow and delicate in the deep, collapses into whiteness. The water becomes thick with suspended grains that reflect any nearby light. Cameras that moments before captured the faint texture of the rocks now see nothing but a glowing haze. The storm does not roar with sound. It has no wind. Yet it blinds everything within its reach as effectively as a snowstorm in the cold of winter. These storms can begin with surprising ease. A robot descending into the trench may approach the floor cautiously, using thrusters to guide the final moments of arrival. But these thrusters stir the water below, lifting sediment in soft plumes. The plumes rise and spread. Within seconds, the view becomes fogged, then lost entirely. The pilot or autonomous system sees only a milky whiteness, a cloud that conceals any detail of the seafloor. It is as though the bottom has vanished. If a thruster is angled even slightly downward, it can carve temporary craters into the soft sediment, pushing clouds outward in all directions. A mechanical arm meant to collect a sample may brush a rock and release a faint swirl that soon becomes a wide drifting sheet. Even the motion of settling onto the ground, where the craft's weight compresses the sediment beneath it, produces a ring of disturbed grains that float upward as though lifted by an invisible hand. Once a silt storm begins, there is almost nothing the crew can do to clear it. The water around the submersible is too still to sweep the particles away quickly. Instead, the storm settles at its own pace, drifting far beyond where it originated. Long after the robot has moved away, the cloud continues expanding, spreading into distant corners of the trench and filling narrow channels with its ghostly shimmer. This is why landing on the seafloor is one of the most difficult tasks in the Hadal world. The bottom is not firm in most places. It is soft and yielding, and the weight of the craft presses into it like a footprint in powder. The disturbance lifts grains into the water, making any precise work nearly impossible. If the submersible hopes to collect samples or observe a creature, it must do so before the first motion stirs the storm. In many cases, explorers never see the true landscape beneath them until they review the brief footage captured in the moments before the touchdown. The risk of sinking into the sediment also exists. In some places, the layers are deceptively deep. A submersible that attempts to rest on them may find itself tilting or sinking slightly, forcing pilots to adjust with careful thruster bursts that only worsen the disturbance. Once the cloud rises, even instruments that rely on reflected light or laser measurements struggle as the particles scatter each signal differently and distort the readings. These silt storms hold another quiet challenge. They can hide hazards. A smooth patch of ground may conceal rocks or steep edges. A cloud drifting along the floor can mask sudden drops or unstable areas where the sediment sits loosely atop buried slopes. Without clear visibility, the submersible must trust its sensors more than its cameras, navigating by touchless readings rather than sight. Even then, sensors can misinterpret the cloud as a solid object or miscalculate distances through the haze. Yet for all their challenges, silt storms are part of the deep sea's character. They reveal how fragile the environment is, how easily its calm can be stirred by even the smallest motion. They remind us that the deep is not a world shaped by speed, but by stillness. Every disturbance leaves a mark that lingers in the quiet water, drifting gently through the darkness until gravity pulls the grains back to rest. In this world where clouds form not from the sky but from the ground, exploration becomes a slow dance. Each movement must be thoughtful, each descent must be careful. And as the soft particles float through the beam of the submersible's light, the deep reminds us once more that even in darkness, the ocean is alive with motion too gentle for the surface to ever witness. As our slow descent continues, the trench begins to reveal life shaped by conditions no human body could withstand. We have traveled through pressure that crushes steel, through darkness deeper than any night, through cold that stills machines, and through waters whose chemistry differs from the seas above. Yet here, in a world where our own physiology would fail in moments, living creatures drift and crawl as though this extreme environment were the most natural home imaginable. Life in the Hadal zone, the deepest region of the ocean, does not resemble the familiar shapes that swim near the surface. Instead, it emerges in forms sculpted by millions of years of quiet adaptation. Some species glow softly, their bodies carrying small reservoirs of bioluminescent chemicals. Others move without any light at all, guided by senses far removed from human experience. Some grow large, taking advantage of the stillness and abundance of sinking nutrients. Others remain small and delicate, conserving energy in a place where food arrives slowly from far above. One of the most remarkable creatures found in these depths is the Hadal snailfish. It is a soft-bodied animal, pale and fragile-looking, yet capable of living nearly 7 miles beneath the surface. Its bones are not hard like those of its shallow-water relatives. Instead, they are reduced to light structures that resist the crushing pressure by bending, not breaking. Its skin appears almost translucent, and its muscles contain special adaptations that allow movement in water so dense it might feel like syrup to creatures from the surface. The snailfish glides through the deep with gentle ease, settling on the soft sediment and feeding on tiny crustaceans that drift along the floor. These crustaceans, too, are adapted to the extreme. Amphipods found in the Hadal trenches often grow larger than their shallow water cousins, their bodies shaped by the high pressure and the availability of organic fragments that fall from above. Their shells contain traces of aluminum compounds absorbed from the surrounding water, which may help protect their bodies from the unusual chemistry of the trench. Their organs operate with enzymes crafted through evolution to function in conditions that would stop most life instantly. The key to survival in this high pressure world lies in proteins, the delicate molecular tools that carry out nearly every biological task. At the surface, proteins fold into shapes perfectly suited for their work. In the deep sea, however, pressure tries to unfold and twist these proteins, disrupting their shapes and preventing them from functioning. Hadal organisms use pressure-resistant proteins, strengthened by special molecules that act like tiny supports. These molecules help keep the proteins folded correctly, preventing them from collapsing under the weight of the water. It is a quiet, elegant solution to a deadly problem, and it allows life to continue where the forces of physics seem overwhelming. Pressure also affects cell membranes, the thin boundaries that encase every living cell. In the deep sea, the pressure would normally force these membranes into rigid forms that cannot flex or allow nutrients to pass through. But Hadal creatures build membranes from different types of lipids, ones that remain fluid and flexible even in the cold and under immense force. These unique structures keep cells alive and functional, enabling growth, movement, and reproduction. Many deep-sea animals possess transparent tissues, a trait that helps them survive in a world where vision becomes obsolete. Without sunlight, the need for pigmentation disappears. Muscles, skin, and even internal organs may become nearly invisible, blending seamlessly into the surrounding darkness. Transparent tissues also reduce metabolic demand, since producing pigment requires energy. In a place where food falls slowly from above, energy conservation becomes essential. Metabolisms in the Hadal zone move at a different pace than those near the surface. Cold temperatures slow chemical reactions, yet creatures here have adapted to operate efficiently in this chill. Some species digest food slowly, extracting every bit of energy from the scarce meals they find. Others rely on symbiotic bacteria to help them process nutrients. A few species gather near hydrothermal vents that lie close to trench regions, using chemicals in the water as a source of energy, a process known as chemosynthesis. These ecosystems rely not on sunlight, but on the deep Earth's heat and minerals, forming quiet networks of life in the dark. Even movement follows new rules here. In the still waters of the Hadal zone, swimming becomes a matter of slow, deliberate motions. Sudden bursts of speed waste precious energy. So many creatures glide, hover, or even let currents carry them. Eyes, when present at all, tend to be small or poorly developed, replaced by sensitive hairs, pressure receptors, or chemical detectors that read the water's subtle changes. Together, these adaptations paint a picture of life that feels otherworldly, yet each creature remains deeply connected to the rhythms of the ocean above. Organic fragments drift downward over weeks, becoming food for communities at the bottom. Tiny particles fall like snow, feeding microorganisms that in turn nourish larger animals. This cycle continues quietly, shaping the Hadal world with a steady flow of life from the sunlit surface. Though humans cannot enter this realm without layers of steel and engineering, life thrives here with simplicity and grace. It has shaped itself to match the deep, becoming part of the pressure, the cold, and the darkness. In this silent region where machines struggle and human bodies cannot endure, these creatures live as naturally as birds in the sky or fish near a coral reef. And so the trench, which seems so alien to us, becomes a home for countless beings that have mastered the art of survival in a world far beyond our reach. As our quiet journey continues along the deepest folds of the ocean, we drift into a realm where life follows rules unlike anything found in the sunlit world above. Until now, our path has carried us through pressure, darkness, cold, and drifting silt. We have seen creatures shaped by these conditions, their bodies translucent and their proteins strengthened against forces that would unravel the cells of surface creatures. But here, near the edges of hydrothermal vents and along the narrow floors of deep trenches, life becomes something even more extraordinary. It is life that does not depend on sunlight at all. On the surface of Earth, sunlight is the foundation of nearly everything. Plants gather it, algae absorb it, and through these processes, energy moves upward into insects, fish, mammals, and eventually into us. The familiar chain of life begins with light. For a long time, scientists believed this rule extended across the entire planet. Without sunlight, there could be no foundation for ecosystems, no energy for growth, and no life sustained by anything other than crumbs drifting from above. But the deep sea, patient and ancient, revealed a different truth. At the edges of tectonic plates, where the Earth's crust stretches and cracks, heat from the mantle rises upward. Water seeps into the seafloor, warms, mixes with minerals, and escapes again through vents as dark, billowing plumes. These hydrothermal vents form small oases in the cold abyss, each one releasing clouds of mineral-rich water that shimmer like smoke under the faint lights of submersibles. Around them, the temperature rises sharply, creating a soft glow of warmth in an otherwise frozen world. In these warm regions, life has found a new beginning, one built not on sunlight, but on the quiet chemistry of Earth itself. The key lies in chemosynthesis, a process both delicate and powerful. Instead of using light to create energy, certain bacteria use chemicals from the vent water, such as hydrogen sulfide or methane. Through intricate molecular steps, they transform these substances into energy that fuels growth. These bacteria become the foundation of entire ecosystems, playing the role that plants and algae play in shallow seas. They form mats on the rocks, coat the surfaces of vents, and even live inside other organisms as internal partners, providing nourishment from within. Around these bacteria rise communities unlike any found in the sunlit world. Tall white tube worms gather near vent openings, standing silently like soft forests. Their bodies contain no mouths and no digestive systems. Instead, they live symbiotically with bacteria hidden deep inside them. These bacteria process chemicals from the vent water, sharing the energy they produce with the worm, while the worm shelters them within its tissues. It is a partnership shaped over millions of years, one that blurs the line between individual and ecosystem. Nearby, giant clams rest on the seafloor, their shells wide and pale. Inside them, bacteria also thrive, converting vent chemicals into a steady source of nourishment. Crabs with pale shells pick their way across the warm rocks, feeding on mats of bacteria or tiny creatures drawn to the heat. Some shrimp species cluster in dense groups, their bodies glowing faintly from reflected light, their eyes adapted to sense the faint warmth of the vents rather than light itself. These ecosystems rewrite what we know about the physics of life. They show that sunlight, though essential in most places, is not the only possible path for survival. The vent communities reveal that life can arise from heat and chemistry alone, shaped by the planet's internal engines rather than by the distant glow of the sun. They suggest that energy can flow from the Earth itself into cells that have never once felt a ray of light. This idea has changed not only our understanding of the ocean, but our understanding of where life might exist elsewhere in the universe. If life can survive here, warmed only by deep rock and fed only by chemistry, then it may thrive on distant icy moons or deep beneath the crust of planets far from our own. Hydrothermal vents also change how scientists think about the origins of life. Some theories now propose that early life may have begun in environments much like these, where minerals, heat, and water met in a quiet union. In such places, small molecules could gather, interact, and eventually form the first stable systems capable of growth. The deep sea, far removed from sunlight, may hold echoes of the world as it was billions of years ago. Yet these vent ecosystems are not permanent. They rise and fall with the shifting of tectonic plates. A vent may remain active for decades or centuries, then fade as the crust changes. When a vent dies, its surrounding community slowly disperses. Tube worms collapse. Bacteria lose their energy source, but life in the deep is resilient. New vents appear elsewhere, and larvae drifting through the dark settle upon fresh ground, beginning the cycle again. In this way, life in the Hadal world moves through time not with the rhythm of seasons, but with the patient pulse of shifting stone. It survives without sunlight, without certainty, and without the warmth of the surface world. It grows in a landscape shaped entirely by the physics of pressure, heat, and chemistry. Here, in the deepest parts of the ocean, life becomes a quiet testament to possibility. It shows that even in the most unlikely places, the earth finds ways to fill the darkness with motion, growth, and the soft persistence of living things. As our journey winds deeper into this quiet world, the landscape below grows more mysterious rather than more familiar. We have followed the pressure, the darkness, the drifting silt, and the strange physics that shape life in the abyss. Now we turn our attention to the trench itself, to the structure that cradles these ecosystems in its cold embrace. It may seem surprising, after decades of science and exploration, that the deepest place on our planet remains imperfectly known. Yet the truth is that the Mariana Trench, with its narrow walls and shifting floor, keeps its shape hidden from us even now. Mapping the trench is a task shaped by difficulty from the very beginning. The ocean absorbs and scatters signals, making even our best sonar feel blind at such depth. Earlier in our journey, we saw how sound moves slowly in cold brine and bends under pressure and temperature. These effects grow stronger near the Hadal floor, where the layers of water change density in ways that distort sonar pulses. A signal sent downward from a ship may travel farther than expected, or drift sideways, or reflect off a steep wall before returning to the surface with a misleading echo. The result is a world of data that often appears incomplete, fragmented, or strangely shaped. Scientists gather these echoes and reconstruct the landscape grain by grain. But the sea is vast, and the trench is long and narrow, stretching across the floor of the Pacific like a deep scar. No single expedition can map it fully. Ships must travel back and forth in long lines, gathering data slowly. Even after many passes, the results contain gaps, places where the signal was too weak, the angle too steep, or the conditions too variable. These gaps become small blank spaces on our maps, tiny windows of uncertainty, but when added together, they form a puzzle far larger than one might imagine. Even the most detailed maps of the trench contain areas where the floor is known only loosely, measured with margins of error far larger than the features themselves. One section may appear smooth and gently sloping, only for later expeditions to find hidden ridges beneath the haze of data. Another section may seem to hold the deepest point until a different survey records a signal that suggests a pocket even lower, tucked between two steep walls. These conflicting measurements are not mistakes. They are reflections of the environment's complexity, a reminder that the deep sea obeys rules we are still learning to navigate. The depth of the trench is not a single number. It is a shifting story that changes as technology improves. Over the past century, instruments have become more sensitive, more stable, and more capable of probing immense depths. Each new generation reveals details that were invisible to the one before. In some years, a new lowest point is announced. In others, scientists revisit old readings and adjust them with fresh insights. These changes are part of the slow unveiling of a place that resists easy understanding. Even now, researchers wonder whether the trench holds hidden pockets that have never been directly measured. The floor of the Mariana is not smooth. It is shaped by geology, by subduction, by landslides, and by the steady drift of sediments. In narrow valleys where sonar beams cannot reach clearly, there may be depressions deeper than any we have recorded. These pockets could be small, only a few hundred meters across, or large enough to form an entirely new deepest point. Their secrecy lies not in their size, but in the surrounding landscape, where steep walls and drifting clouds of sediment cloak them from the tools we use to explore. Some of these possibilities arise from the nature of subduction itself. The trench forms where one tectonic plate bends and slides beneath another. This bending does not create a smooth curve. It produces fractures, shelves, and sudden drops. In certain places, the descending plate may fold more steeply, forming narrow plunges that sonar barely touches. In others, sediment carried by underwater landslides may conceal deeper holes beneath a layer of soft material. Even a thick blanket of silt a few meters deep can raise the apparent floor of the trench, hiding the true stone beneath. Scientists approach these mysteries with patience. Each expedition adds a few more pieces to the puzzle. Some carry deep-sea landers that drop to the floor and record depth directly. Others use autonomous vehicles to weave through the narrow spaces where ships cannot send clear signals. These missions provide glimpses of the real landscape, but they cannot cover the entire trench. The area is simply too vast, and the sea too unpredictable. The possibility of undiscovered depth remains one of the trench's quiet secrets. It does not imply dramatic new extremes. Instead, it reminds us that the ocean's deepest world is shaped by forces that move slowly and leave features too hidden for broad sweeps of sonar. It suggests that beneath the water's weight, the earth holds creases and folds that require time and careful observation to understand. As we drift through this section of our journey, the trench becomes not just a place, but a reminder of the limits of perception. We know its length in broad strokes, its general shape, its steep walls, and its cold floor. Yet the fine details, the exact contours, the pockets of unusual depth, remain just beyond reach, waiting for new tools or new patience to reveal them. And so the trench carries its shape in quiet mystery, a landscape that keeps part of itself hidden, held gently in the deep where light never travels and where only the most persistent echoes return. As our quiet exploration continues deeper into the trench, we reach a point where the pressures outside no longer feel like numbers or measurements. They become a presence, a slow and steady weight that shapes everything it touches. Earlier, we followed how this weight tests the limits of machines, of vessels, and of the delicate systems that support exploration. Now we look even closer, into the materials themselves, into the way the deep reshapes matter with a patience that feels almost geological. Down here, nothing behaves as it does at the surface. Metal, ceramic, plastic, and composite materials all take on new personalities under the immense weight of the Hadal world. The deep ocean does not crush instantly, except when a flaw or weakness reveals itself at once. More often, it shapes and shifts the materials around it through slow force. This process is known as plastic deformation, a quiet bending of the very structure of solid matter. Unlike sudden fractures, plastic deformation begins subtly. The pressure presses atoms closer together, encourages bonds to rearrange, and nudges the material into forms it was never meant to hold. At the surface, metals and other solids return to their original shapes when pressure is removed. In the trench, they do not. The deformation becomes permanent, leaving a story of stress written into the material's body. Even thick metal walls, carefully shaped and tested, begin to yield under this constant weight. A sphere that looks perfectly round before the dive may come back slightly distorted. A cylindrical section may develop gentle flat spots or slight compressions that cannot be seen unless measured with precise tools. These changes do not always cause immediate failure. Instead, they accumulate over many dives, each descent adding another subtle shift until the structure finally reaches a point where it can no longer resist the pressure. The failure may occur suddenly, but the origin lies in the long, slow bending that began from the first moment the vessel touched the deep. Different materials respond to pressure in their own ways. Metals, for example, are known for their strength and for their ability to bend without breaking. This makes them ideal for deep sea exploration, where flexibility matters as much as hardness. Steel was used in early submersibles because it could endure great pressure and because it bent gracefully under stress. But steel is heavy, and as engineers reached for greater depths, they sought stronger and lighter alternatives. Titanium became the metal of choice for many modern deep-sea vessels. It is lighter than steel, resistant to corrosion, and extraordinarily strong. It can withstand forces that would crush other metals into fragments. Yet even titanium is not immune to the slow influence of the Hadal world. Under repeated dives, titanium spheres and hulls develop microscopic fatigue marks, tiny imperfections that slowly grow. These imperfections may begin as harmless patterns of stress, but over time they become points where pressure can concentrate. Each dive, each change in temperature, and each shift in pressure adds a little more strain. Eventually, even titanium must acknowledge the deep. Ceramics behave differently. They are often extremely hard, capable of resisting scratches and deformation at the surface. Ceramics also handle compression well, far better than they handle bending or stretching. In a perfect world, a ceramic sphere could support incredible pressure, but the deep sea is not a perfect environment. Ceramics tend to be brittle, meaning that once a crack begins, it travels quickly. A ceramic material placed in the trench may hold steady for a while, but a single flaw, invisible to the eye, can cause it to shatter suddenly. This is why ceramics are used sparingly in deep-sea vessels, often as components rather than as the primary structure. Their strengths are magnificent, but their vulnerabilities make them risky in a world where even the smallest flaw can grow under pressure. Plastic materials, though seemingly weak compared to metals and ceramics, have their own role in deep-sea exploration. Certain polymers remain flexible at extreme depths, bending instead of shattering. Yet plastic also undergoes deformation. It stretches, compresses, and changes shape under continuous pressure. The deep can make plastic brittle over time, causing it to crack or lose its ability to cushion other materials. It can also cause plastic to swell, altering its fit within a system. These changes often go unnoticed until a component fails or a seal no longer sits as tightly as it once did. Composite materials attempt to combine the strengths of metals, plastics, and fibers. These advanced structures can be both strong and lightweight, Some are used in deep sea floats or in outer casings of experimental robots. But composites, too, face the same enemy. Pressure works through the layers, seeking weak points, testing the bonds that hold the different materials together. A composite that endures one dive may delaminate on another, the layers beginning to peel apart internally as pressure infiltrates their structure. Time is the deep sea's most reliable partner. A vessel may resist the pressure for a single dive, or even several, but repeated exposure wears down even the strongest materials. The deep does not rush this process. It presses steadily, day after day, year after year, reshaping matter with a quiet patience. The metal remembers each dive. The ceramic records every tiny imperfection. The plastic carries the memory of every stretch and compression. The trench alters them all, turning each journey into a subtle conversation between human engineering and the Earth's immense forces. In this world, strength is not simply a matter of hardness or weight. It is a question of endurance, resilience, and the ability to bend without breaking. Even the most advanced materials on Earth must approach the trench with respect, knowing that the deep sea will test them not with violent attacks, but with slow, steady pressure that never relents. As our journey drifts deeper into the quiet folds of the trench, we begin to see that pressure is not the only force shaping what survives here. Even the strongest metals, the smoothest plastics, and the most carefully designed instruments are slowly changed by the deep ocean in ways that feel almost alive. The deep does not simply surround technology, it interacts with it, alters it, and sometimes consumes it. In this place where light never reaches and cold water settles with heavy patience, the ocean reveals another one of its ancient talents. It eats. Corrosion, one of the earliest challenges faced by explorers, begins long before a vessel reaches the Hadal world. At the surface, metal meets oxygen-rich water, and a slow reaction begins. But near the bottom of the trench, the chemistry changes in quiet but powerful ways. Salts linger in high concentration, particles drift through the water like forgotten dust. Tiny differences in temperature and pressure set off reactions that move across the surface of metal with steady determination. Corrosion is often imagined as rust, an orange coating on old iron left in the rain. But in the deep sea, it takes many forms. Some metals pit, forming small cavities that deepen over time. Others form thin layers of oxide, protective at first, but vulnerable in areas where the layer cracks. A small imperfection becomes an entry point for salt water. Once inside, the water begins to change the internal structure of the metal itself. No dramatic cracks appear right away. Instead, the metal weakens slowly, like wood softened by years of rain. Electrochemical reactions advance this process. In the ocean, minerals move through water as charged particles. When these particles meet a metal surface, they cling, react, or exchange electrons. Different metals interact in different ways. If two metals are placed close together, the ocean can turn them into a tiny battery. One becomes the anode, losing atoms to the water. The other becomes the cathode, protected for a time. This is known as galvanic corrosion, and it can destroy bolts, joints, or fasteners with surprising speed. A single submersible is often built from many metals. Titanium may form the pressure hull, steel may form the landing skids, aluminum might be used for internal structures. Each metal behaves differently when touched by seawater. The deeper the submersible descends, the more the pressure changes the water's behavior. Ions move more slowly, reactions unfold at different rates. Time stretches out in the cold, giving each electrochemical process a chance to burrow deeper into the material. Insulation helps. Protective coatings slow these reactions, but they cannot stop them completely. A scratch in the coating, invisible to the eye, becomes a starting point. The ocean presses into that spot, encouraging reactions that move outward in faint patterns. After many dives, engineers find small pits where smooth metal once existed. These pits are more than surface marks. They weaken the structure, changing how it handles stress under pressure. Even materials designed to resist corrosion cannot escape the ocean completely. Titanium, for instance, forms a protective oxide layer that keeps oxygen from reaching the metal beneath. But if that layer is disrupted, even slightly, the deep sea begins its slow work. The process may take years, but it happens with the certainty of tides. The trench does not need speed, it has time. Beyond chemical reactions, the ocean hosts life forms that interact with technology in quieter but equally persistent ways. Biofouling, the growth of organisms on surfaces, is often associated with shallow water where barnacles, algae, and small crustaceans gather. But the deep sea has its own form of biofouling. Though oxygen is scarce and light non-existent, bacteria and other microorganisms still attach themselves to surfaces. They settle in thin layers, forming films that can change how a sensor reads the water or how a light reflects off its surroundings. In the Hadal zone, these organisms grow slowly, almost imperceptibly, yet over time, their presence alters the performance of instruments. A sensor coated in microbial film may drift in accuracy. A camera lens touched by bacterial growth may cloud or scatter the faint light it captures. Even the smooth surfaces of floats or containers may become textured with thin layers of living cells, changing how they behave in water that demands precision for buoyancy and balance. Some bacteria contribute directly to corrosion. They form communities on metal surfaces and create microenvironments that accelerate reactions. Their metabolic byproducts, though tiny in amount, can change the pH near the metal, encouraging slow but steady decay. These organisms live at pressures that would destroy other forms of life, yet they thrive on the surfaces of machines built to explore the deepest places on Earth. As submersibles rise from the trench after a long mission, the marks of the ocean become visible under bright laboratory lights. Thin webs of film, small pits, faint discolorations, metals that once shone like mirrors now hold a matte finish that tells the story of chemical interactions in the dark. Engineers clean, repair, and strengthen these machines, preparing them for another descent. But each journey adds a new layer of wear, another subtle memory etched into the surface. The ocean does not devour technology quickly. It works with immense patience. Pressure begins the shaping. Chemistry continues it. Life adds its own threads to the process. Together, these forces create a world where even the strongest devices must accept that they are temporary visitors, not permanent residents. In this deep, silent realm, the ocean becomes both environment and sculptor, touching every surface with the slow artistry of time. As we continue drifting through this hidden world beneath the waves, the senses we rely on at the surface begin to loosen their familiar shape. Down here, sight and sound behave like wandering travelers, bending and shifting under the pressure of the deep. Machines designed to measure light, distance, and direction find themselves working in a landscape where the very fabric of perception becomes fluid. Vision is softened by darkness. Sound is stretched by cold water and shifting pressures. Every signal must travel through a realm that reshapes it gently but relentlessly. In the upper ocean, Light behaves in predictable ways. It bends through the water at angles that allow fish to see approaching shapes, and it supports the colorful glow of corals and drifting life. But as we descend into the deeper world, the rules begin to shift. The water becomes denser, temperatures sink, particles float in the silence like drifting threads of silk. When light enters this space, it no longer moves in straight lines. It bends, it slows, it refracts. Refraction is a quiet distortion. It happens wherever light passes from one medium into another. On the surface, we see it in the wavering edges of a straw inside a glass of water. In the deep sea, this effect is magnified by pressure and cold. Even a small change in temperature can cause light to bend at different angles. A camera looking forward may see a world that appears slightly stretched. A circular object may look oval. A straight ridge along the seafloor may shimmer as if it is curving. These distortions may seem small, but they matter. Submersibles depend on cameras for navigation in the dark. Robots use lasers to measure distance. A faint refraction error can shift a measurement by hundreds of centimeters. Each change in water temperature, however slight, alters the path of light. The machinery continues to record faithfully, yet the environment reshapes the story it receives. Sound behaves differently, but it also bends under the weight of the trench. Earlier, we listened to the soundscape of the abyss, where whale calls glide through the dark and tectonic murmurs drift like ancient songs. But for explorers, sound is more than atmosphere. It is the primary tool for understanding what lies ahead. Sonar sends pulses into the water, waiting for the echoes to return with information about distance and shape. In the deep, these echoes become unreliable narrators. Cold water slows the speed of sound. Dense water bends it. Layers of changing temperature refract it, just as they refract light. A single pulse of sonar may travel in arcs instead of straight lines, touching the seafloor at angles the machine does not expect. When the echo returns, the timing is shifted, the direction is altered. The landscape appears different than it truly is. Sometimes, the echo splits into several parts, each one bouncing back from a different slope or drifting through different layers of water. The machine captures all of these echoes, but it cannot immediately tell which one is true. The deep sea fills the map with uncertainty, drawing shadows on the edges of every measurement. Distorted echoes can even create illusions. A small rock may appear enormous, a gentle slope may seem like a steep cliff, an empty space may look like a solid wall, or a solid wall like an empty space. For a robot navigating narrow canyons in the trench, these illusions add quiet risk. What appears safe may not be. What seems near may be far away. The deep sea holds its landscapes behind layers of shifting sound. Sensors face another challenge. In the upper world, they measure temperature, pressure, and direction with steady accuracy. But extreme cold changes the behavior of electronics. Circuits respond more slowly, batteries weaken, the fine materials inside sensors contract under pressure, altering how they interpret the surrounding world. This leads to sensor drift, a subtle wandering of the machine's readings. A compass may tilt a little. A thermometer may report a value slightly off. A pressure gauge may shift by a few tenths, then a few whole units. None of these errors begin dramatically. They grow quietly, influenced by the cold and the crushing weight. As the machine sinks deeper, these small drifts stack together, shifting the submersible's understanding of where it is and what surrounds it. Engineers compensate for these changes as best they can. They design instruments with thicker walls, reflective surfaces, and protective housings. They test electronics in pressurized chambers and adjust for drift with careful calibration. Yet, even with these precautions, the deep still places its touch upon every measurement. It is not a hostile touch, it is a natural one. Light bends because the water grows dense. Sound stretches because the cold slows its pace. Sensors wander because materials change shape under pressure. The deep sea simply behaves according to the physics of its realm, and in doing so, it reshapes what we see and hear. This world is not easy to understand, but it is beautifully consistent in its own way. Every distortion, every echo, every drifting signal is part of the quiet conversation between matter and depth. And as we follow our slow descent through these layers of shifting perception, we learn that even our most trusted tools must adapt to the deep or risk losing the shape of the world entirely. As our quiet descent carries us deeper into this world shaped by pressure and darkness, another challenge slowly emerges, one that is less dramatic than crushing force or corrosive chemistry, but just as limiting. It is the challenge of finding direction in a place that offers no fixed point to follow. On land, we navigate by mountains, trees, and distant skylines. At the surface of the ocean, we follow stars, waves, and satellites that guide us with calm precision. But in the deep sea, none of these companions exist. The landscape stretches out in shadow. The currents move like wandering rivers, and the tools that guide us on the surface fall silent. The seafloor near the trench is a world shaped by immense pressure and geological forces, yet its appearance is deceptively simple. Much of the terrain is smooth and soft, sculpted by sediments that drift down from the surface over centuries. In some places, steep walls rise like ancient cliffs; in others, narrow valleys cut between them. But in many areas, the landscape holds no clear structure at all. The floor becomes a gentle plain without hills or distinctive formations. Cameras that struggle to see more than a few meters reveal only faint outlines of sand-like silt and scattered stones. To a submersible, this world offers no landmarks. There are no ridges to follow, no tall formations to circle, no bright features to mark progress. The terrain could repeat itself endlessly without revealing any familiar pattern. A machine drifting even a short distance from its intended path may find itself in a landscape that looks identical to where it began, with nothing to hint at direction or position. Navigation becomes a delicate art, dependent on memory, sensors, and careful planning. But the deep sea adds more challenges to this process. Water in motion, though invisible to cameras, constantly reshapes the path of a submersible. Currents at the surface are easy to feel. In the deep, they move more slowly, but they never stop. A gentle flow can push a submersible sideways for minutes before any instrument notices. By then, the craft may have drifted far from its intended route. These currents are not always predictable. Layers of temperature and pressure shape them into winding streams that move at different speeds. A submersible passing through one layer may find itself drifting north, then moments later crossing into another that pulls it east or downward. Thrusters correct the motion, but only when sensors detect the drift. And once detected, the correction may already require precious power, time, and care. Thrusters themselves are limited tools in this silent world. They push against a dense, heavy medium that resists sudden changes in motion. A small correction can take many seconds, and during that time, the current continues to pull. The sub becomes a quiet dancer moved by water it cannot see. Because the terrain offers little guidance and currents shift the path, explorers often rely on instruments to track position. These instruments can measure headings, distances traveled, and changes in depth. But instruments drift over time. Compass readings shift under metallic influence. Distance calculations depend on sensors that are subtly altered by pressure. Slowly, the map in the machine's memory begins to diverge from the world outside. At the surface, navigation satellites orbit Earth in gentle precision, allowing ships and aircraft to know their location within moments. Global positioning signals reach across continents and oceans, tying every point on Earth to a digital sky. But these signals cannot travel through seawater. Even a few meters of water block them. The deep ocean, shielded by kilometers of dense, moving saltwater, remains totally beyond their reach. Without GPS, a submersible cannot know its exact location. It must piece together its path from internal readings, sonar reflections, and estimates of drift. The deeper the descent, the more complex this process becomes. A slight error early in the journey grows larger as the dive continues, spreading uncertainty across every direction. Some missions use long cables that connect the submersible to a support ship on the surface. These cables carry data and power, and they help track the craft's position. But the cables themselves are heavy and vulnerable to currents. They form long arcs in the water, adding their own shifting weight to the system. As the sub moves, the cable moves behind it in slow, unpredictable patterns. The position estimate becomes a blend of known and unknown forces, each shaping the craft's path through the dark. Untethered robots rely completely on their onboard systems. They drift, measure, adjust, and hope that their understanding of their surroundings remains true. After many hours, they rise back to the surface, carrying maps that may hold distortions shaped by currents and drifting sensors. Engineers must then interpret these maps, smoothing errors and comparing them with previous journeys to find patterns. Navigation in the trench is like tracing a path through a dream. Shapes shift, currents guide without warning. Light fails to reveal more than a few meters. The ground offers no direction, and the sky, filled with satellites, remains impossibly far away. Yet even in this quiet chaos, explorers continue to send their machines downward, trusting in their slow, patient instruments to guide them through a world where the familiar idea of direction softly dissolves into the deep. As our quiet journey continues into the deepest realms of the ocean, we reach a place where exploration becomes more than an engineering challenge. It becomes a careful dialogue with uncertainty. Every dive into the Hadal world carries a weight that is both literal and symbolic. Submersibles, crafted with precision and hope, descend into a realm that keeps secrets even from the machines designed to reveal them. And sometimes, those machines never return. Across decades of exploration, there have been moments when probes, robots, and experimental vehicles were released into the trench with confidence, only to vanish into the silent dark below. Some of these machines failed suddenly, others drifted off course. A few simply disappeared without a single signal returning to the surface. Their last transmissions came as faint blips, then silence. The ocean did not crush them dramatically or swallow them violently. It simply closed around them and kept them. These losses are not rare, though they are rarely spoken of outside scientific circles. They are reminders of the strange shaping forces we have seen in earlier sections. Pressure that bends metal, darkness that blinds cameras, currents that pull machines from their planned descent, sediment clouds that hide obstacles, sound waves that return distorted echoes, sensor drift that erodes certainty. Each challenge alone makes deep-sea navigation difficult. Together, they become the reason retrieval is nearly impossible once a machine is lost. When a submersible disappears in the trench, finding it again becomes a task shaped by the same forces that caused its disappearance. The terrain holds few landmarks, and any marks a vehicle leaves in the soft sediment fade quickly as particles drift and settle. Even if the craft comes to rest on the seafloor, no plume or ripple rises to mark its presence. It becomes part of the stillness, silent and unmoving. The water column above it acts like a vast curtain. Radio signals cannot pass through even a small portion of the ocean, and communication cables only reach where the craft allows them to. A disconnected submersible carries no beacon that can pierce the kilometers of dense, shifting water above. The deep does not permit bright flares or emergency lights to call for rescue. Everything that could guide a search remains sealed beneath cold layers of water that scatter and distort every form of signal. Even if explorers know the general area of the loss, the search cannot rely on GPS or visual scanning. Instead, they must deploy sonar, which struggles with the terrain we have visited earlier. Refraction bends sound waves. Distorted echoes paint confusing shapes on screens. The slope of the trench walls scatters signals, sending back faint outlines that could mean anything. A search might last hours or days, with each ping of sonar creating more questions than answers. And even if a craft were found, retrieval presents its own near impossible challenge. Machines designed to reach the seafloor can descend safely, but may not have the strength to lift another vehicle from the trench floor. The pressure at 11,000 meters crushes every object with a weight that no simple mechanism can resist. To lift a lost submersible, engineers would need a machine capable of supporting the weight of the vehicle, the pressure acting on it, and the forces created by ascent. Such a rescue craft would need to be larger, stronger, and more costly than the vehicle it was trying to save, and it would face the same risks of failure. Recovering even a small probe could take many months of planning and millions of dollars, all with the possibility of losing yet another machine. The financial cost alone shapes the choices scientists make. Deep sea probes are not simple devices. They are the product of years of research, custom materials, and specialized components built to survive a world that resists being touched. Losing one means losing not only the physical craft, but also the thousands of hours invested in designing it. Funding agencies must weigh the cost of replacement against the uncertain rewards of future dives. But the scientific cost cuts even deeper. Many of these lost probes carry data that can never be recovered. Temperature profiles of the trench, samples of sediments that may contain ancient clues, recordings of new species or chemical interactions, maps of regions that no camera has ever seen. When a submersible disappears, so does the information it gathered, held only for a moment before being swallowed by the dark. In some cases, missions designed to answer specific scientific questions are halted for years because the data needed to guide the next step was lost with the vehicle. The loss also affects future exploration. Engineers must redesign vehicles, sometimes starting from the beginning. Teams must adjust their expectations, choosing safer routes or less ambitious goals. The memory of a vanished submersible becomes part of the story of the trench, shaping the limits of what researchers attempt. Yet, despite these risks, explorers continue to send machines into the abyss. Each dive is a quiet step into the unknown. Each probe is a fragile vessel carrying curiosity into a world that has never offered certainty, and each loss, though costly, becomes part of the deep ocean's lesson. It reminds us that the Hadal realm is vast, shifting, and patient, and that every descent into its silence must be made with humility. The trench does not reach upward or pull anything downward. It simply receives whatever enters it. Some machines return, touched but intact. Others rest forever on its soft, cold floor, hidden somewhere in the stillness where light and memory cannot follow. As our quiet journey continues through the deep ocean, a gentle truth becomes clearer with every descent. For all the challenges we have seen, for all the pressures and shifting landscapes and vanished signals, there is another layer to this story, one that reaches far beyond engineering and into the way we choose to explore our world. Human beings have sent probes to distant planets, landed rovers on Mars, and mapped the surfaces of moons that hang like tiny lanterns in the night sky. Yet the oceans of our own planet, especially the darkest trenches, remain only partially known. It may seem strange that a distant world, sitting millions of kilometers away, could be easier to study than the water below our feet. But as we move deeper into the trench, the reasons reveal themselves like slow rising shapes in the dark. Every challenge in the deep sea becomes part of a tapestry that explains why progress here, though steady, is gentle and slow. The first thread is cost. Sending a probe to Mars is expensive, but much of the expense comes in a single burst, a few years of design, followed by a single, spectacular launch. After that, the craft glides through space with no weight pressing on it, no currents pushing against it, and no endless pressure threatening to bend or crush. Once in orbit or on the surface, the vehicle can rely on stable conditions. Temperatures shift, winds rise, but nothing compares to the immense weight of water pressing on every surface of a deep sea machine. Meanwhile, deep sea exploration demands vessels built from rare metals, strong composites, and carefully shaped spheres that must survive 10 or 11 kilometers of water above them. Every component must endure tension, corrosion, and cold. The cost of each dive grows far beyond the construction of the vessel itself. Ships must be hired, crews must be trained, weather at the surface must be monitored. Every descent relies on perfect conditions, and even then, the risk of loss always remains. Where space offers open silence, the ocean offers resistance at every turn. Engineers must build equipment not only to gather data, but to survive its own journey. This makes each mission far more expensive than its equivalent in space, where a probe may function for years with little maintenance. A deep sea submersible requires continuous care, replacement of worn parts, and long periods of testing before every dive. Beyond cost, there are engineering constraints unique to the oceans. In space, the challenge is emptiness. In the deep sea, the challenge is presence. Water surrounds everything. It presses, cools, corrodes, and slows. Electronics must be sealed in protective housings. Batteries lose efficiency in the cold. Lights barely reach beyond a few meters. Thrusters fight not against vacuum but against dense, slow-moving currents. Every movement demands energy. Every sensor must fight distortion. Space probes communicate freely, sending signals across millions of kilometers with clarity. In the deep sea, signals vanish within meters. Satellites cannot penetrate the water. Radio waves fade instantly. Only sound can travel, and even that sound bends and echoes in ways that confuse the most advanced computers. A rover on Mars can send engineers a clear message about a small pebble sitting at its feet. A deep-sea robot may struggle to send a single line of data across a short distance. In this way, the deep sea remains a world where both the medium and the darkness themselves slow exploration. Machines here must carry all the energy they need. They must protect themselves not only from failure, but from the constant reshaping force of the water around them. And so we come to a quiet truth, one that surprises many who hear it for the first time. Mars, with all its storms and cold deserts, is easier to map than Earth's oceans. Satellites orbit Mars without risk, taking photographs from far above. Light passes through the thin atmosphere without distortion. The surface remains still for centuries. A camera can see for kilometers. A radar pulse travels clearly across open land. Earth's oceans, by contrast, hide their floors beneath many layers of water that swallow light and bend sound. A satellite can measure the slight rise and fall of the ocean surface, but the true shape below remains blurred. Every attempt to map the seafloor requires instruments that travel close to it, instruments that must withstand the very forces they are trying to study. The deeper the ocean, the harder it becomes to see clearly. And so the maps remain incomplete, stitched together from brief windows of visibility. This does not mean that the deep is beyond our reach. It simply means that it invites patience. While Mars sits quietly and awaits every photograph, the ocean shifts and murmurs and changes shape. It holds its mysteries not out of hostility but out of sheer complexity. It asks explorers to move slowly, to respect the physics that shape its depths, and to accept that progress will come in small steps rather than sudden leaps. With each dive, we learn a little more, gather a little more data, and bring home another piece of the puzzle. The deep sea teaches us that exploration is not always a race. Sometimes it is a long conversation with a world that speaks in pressure, darkness, and quiet movement. And through that conversation, even at a slow pace, we discover new parts of our planet that remind us how vast and wonderful it truly is. As our journey continues through the quiet immensity of the trench, the challenges we have seen begin to paint a picture that is both humbling and inspiring. Every obstacle, from pressure that bends metal to currents that steal direction, has shaped how we explore the deep ocean. Yet, these challenges have also guided the imagination of engineers and scientists who refuse to let the darkest places on Earth remain forever unseen. In laboratories scattered across the world, new technologies are being shaped with patience and dedication, each one designed to bring us a little closer to understanding the Hadal realm. One of the most important breakthroughs lies in the idea of pressure-neutral electronics. For decades, electronics have been protected inside thick metal spheres, each sphere shaped to resist the crushing force of the deep. These protective shells are marvels of engineering, but they limit how many instruments can fit inside, add tremendous weight, and create a delicate dependence on flawless construction. If even a single hairline flaw appears, the pressure will exploit it. Pressure-neutral electronics work differently. Instead of resisting the pressure, they accept it. The idea is simple yet profound. Instead of sealing circuits within an air-filled chamber, the components are immersed in a fluid or gel that does not compress under pressure. This allows the electronics to experience the same external forces as the surrounding water without collapsing. It removes the need for thick metal walls and opens the possibility of smaller, lighter, more flexible robots. These pressure-tolerant materials must be carefully chosen. The fluids that surround the electronics must remain stable under extreme cold and crushing force. They must not react with the delicate components inside. And they must flow in a way that protects without damaging. Designing such systems requires a deep understanding of both chemistry and engineering. Yet researchers continue to refine them, shaping circuits that can hum quietly at depths where pressure would flatten solid metal. Alongside electronics, another material is helping us descend further into the Hadal world. Syntactic foam, a blend of resin and tiny hollow spheres, offers buoyancy in the deep where traditional flotation materials would crush like dry leaves. Each hollow sphere, often made from glass or ceramic, can withstand enormous pressure. When these spheres are mixed into a stable resin, the result is a material that floats even at the deepest known points on Earth. The beauty of syntactic foam lies in its balance. It is strong enough to resist deformation, but light enough to lift heavy machinery back toward the surface. Engineers use it to keep robots neutrally buoyant, allowing thrusters to work efficiently without wasting power. The foam must be crafted with extreme care. If the tiny spheres are too large or too thin, they may crack under pressure. If they are packed too tightly, the foam becomes heavy. But when the mixture is just right, the foam becomes a lifeline that holds machines steady in the shifting layers of the deep. New versions of syntactic foam are being designed to endure even greater depths. Some use spheres made from advanced ceramics, shaped with more precision than anything created in earlier decades. Others incorporate experimental materials that reduce weight while increasing strength. These foams will allow future explorers to send instruments deeper, longer, and with greater reliability. With stronger foams and pressure-neutral electronics, a new generation of autonomous Hadal robots is beginning to take shape. Unlike earlier submersibles that rely on surface ships, cables, or human pilots, these robots are designed to move through the trench on their own. They glide through the darkness like quiet messengers, gathering samples, mapping landscapes, and listening to the ocean's soundscape without the need for constant supervision. These robots must think for themselves in a world that bends light, warps sound, and shifts their path with unseen currents. Engineers are teaching them to interpret sonar echoes more intelligently, to recognize the difference between drifting sediment and solid ground, and to adapt their course when currents tug them away from their mission. Some future designs allow these robots to work together in small groups. They share information like a school of fish, each one contributing to a larger picture of the world around them. To survive the cold of the deep, their batteries must be improved. Researchers are exploring power systems that resist freezing, circuits that maintain efficiency in near freezing brine, and energy storage methods that work even under the crushing weight of the trench. Some designs borrow ideas from marine animals, storing chemical energy in flexible structures that mimic biological processes. There is even progress toward robots that can anchor themselves briefly on the seafloor, using soft mechanical limbs that bend instead of break. These limbs can press gently into sediment without stirring silt storms. They allow robots to remain still while recording data in the absolute quiet around them. All these technologies share a single purpose. They move exploration away from single, fragile descents toward a future where the Hadal zone can be studied patiently and continuously. Instead of sending one machine into the deep every few years, we may one day send dozens or even hundreds, each one designed to survive and learn in a world that has remained mostly untouched. The trench will never be a place of easy exploration. It will always shape the machines we send. But with each new breakthrough, we move closer to a time when the deep can share its secrets, at a pace guided not by fear or caution, but by quiet curiosity and enduring wonder. As our quiet descent through the deep ocean continues, we arrive at a point where the story turns toward the rare moments when humans and machines have successfully touched the deepest places on Earth. These dives, scattered across decades, are small in number yet enormous in meaning. Each one has carried a single vessel into the Hadal world, allowed it to rest briefly on the seafloor, and brought it safely back to the light. And in those few hours on the bottom, these missions have gathered knowledge that reshaped our understanding of Earth's most hidden frontier. The first lessons came from simple observations. When the earliest deep diving crafts touched the trench floor, their lights illuminated a surface that was softer and finer than many expected. The sediment lay in delicate layers, shifting with the slightest disturbance. It flowed like a slow snowfall pressed into stillness, made from grains that had drifted down over centuries. This soft terrain confirmed that the trench is not only shaped by pressure and geology, but also by the gentle rain of organic debris that falls through the water column year after year. Marine snow, composed of tiny fragments of life, collects here in astonishing quantities, nourishing organisms adapted to harvest nutrients in the cold dark. Life itself became one of the greatest discoveries. Early expeditions brought back images of small, ghostly animals that lived in the Hadal zone. Amphipods, shrimp-like creatures with translucent bodies, moved with ease through water heavy with pressure. Some were larger than their relatives in shallower water, as if the deep gave them space to grow. Others were tiny, clinging to the floor with delicate limbs designed for a world without light. Decades later, newer dives revealed snailfish with soft, flexible bodies, their bones reduced to gel-like structures that could withstand the immense weight above them. These creatures proved that life thrives even in an environment that seems far beyond the limits of biology. Chemical clues emerged as well. Samples of sediment brought upward showed unusual concentrations of compounds created by microbes that survive without sunlight. These microbes feed on chemicals released by the shifting crust beneath the trench. Their presence revealed that the trench is not only a graveyard for drifting debris, but also a cradle for microscopic life that reshapes the ocean's chemistry. Some of these organisms break down substances that would remain stable elsewhere, transforming minerals and carbon deep within the seafloor. The dives also documented geological activity that had only been guessed at before. Instruments placed on the trench floor recorded subtle movements of the Earth's plates. Tiny shifts, nearly imperceptible in the moment, traced the slow descent of the Pacific plate beneath its neighbor. These movements confirm that the trench is not merely a deep valley but a dynamic boundary where the planet's crust folds and sinks. Each measurement helped refine our understanding of earthquakes, volcanic activity, and the slow breathing of the Earth's interior. Yet for every answer, the trench offered new mysteries. Cameras recorded strange shapes drifting through the water, too distant or faint to identify. Some were likely sediment clouds or small creatures moving beyond the reach of the lights. Others lingered at the edges of vision, stirring quiet speculation among researchers. Instruments detected low-frequency sounds that still defy clear explanation. Some pulses matched known tectonic movements. Others came in rhythms that did not align with any familiar natural process. And certain regions of the trench remain unmeasured, forming pockets that may be deeper than the places we currently call Earth's lowest point. One of the most remarkable discoveries came not from biology or geology, but from the engineering challenges themselves. Each successful dive revealed flaws in our designs, and each flaw guided the creation of stronger, smarter vessels. When early submersibles struggled with buoyancy, engineers learned to craft better syntactic foams. When cameras fogged or cracked under pressure, new housings were developed from materials that could flex rather than shatter. When thrusters failed in dense water, more efficient propulsion systems were created. Every triumph and failure became part of the quiet conversation between technology and the ocean. The introduction of advanced sensors transformed later missions. High-resolution cameras captured details of the seafloor that had never been seen before. Chemical samplers collected fluids from micro cracks in the crust, revealing the hidden currents that move beneath the trench floor. Pressure-neutral electronics allowed robots to stay longer at great depths, gathering continuous data rather than brief snapshots. These improvements gave scientists time to observe natural patterns, from slow drifting currents to subtle shifts in water chemistry. Some missions even left instruments behind. These devices remained in the deep for months or years, listening to the Earth's rumbles and watching the slow settling of sediment. When recovered, they brought back long records that allowed researchers to witness how the environment changes across time, not just in the brief window of a dive. Each journey downward became more than an exploration. It became a lesson. The trench taught us that Earth still contains places that resist easy understanding. It taught us that life finds ways to survive in forms that stretch the limits of what we once believed possible. It taught us that the crust beneath the ocean is alive with movement, reshaping the planet in silence. And it taught us that every advance in deep sea engineering requires humility, patience, and immense care. These dives, though rare, have opened windows into a world that remains mostly unseen. Through them, we gather knowledge piece by piece, held gently in the hands of machines that return from the darkness carrying stories written in water, pressure, and time. As our quiet path through the deep continues, we come to a place where knowledge gently fades into uncertainty. Everything learned from the few successful dives offers only a glimpse, a small window into a world so vast that even its edges remain out of reach. The Hadal realm, with all its pressure and darkness, still holds more secrets than discoveries. It is a place where questions drift like the slow fall of sediment, settling softly on landscapes we have never seen. In these depths, life, geology, and unseen corridors of the seafloor continue to guard their stories with calm patience. One of the most enduring mysteries lies in the biology of the trench. Although some creatures have been photographed or collected, the number of known species remains only a tiny fraction of what may exist. The deep ocean hides life forms that do not resemble anything on the surface. Soft-bodied snailfish, transparent amphipods, delicate sea cucumbers that flutter like leaves, and microorganisms thriving in environments rich with pressure and poor in light all suggest that the trench houses ecosystems unlike any found elsewhere on Earth. Yet even these known creatures reveal only the beginnings of understanding. Many possess adaptations that challenge biology itself. Their tissues, for instance, contain pressure-resistant proteins that keep their cells from collapsing. These molecules, shaped by millions of years of evolution, protect delicate structures that would otherwise flatten or fracture. How these proteins function at such extremes remains only partially understood. Their chemistry hints at possibilities that stretch far beyond deep ocean life, offering clues about how organisms might survive on icy moons or other planets where pressure reigns. Among the sediments, microbes live in layers untouched by sunlight for ages. They feed on chemical gradients rather than organic matter from the surface. Some metabolize methane. Others draw energy from minerals released by the shifting crust. Entire microbial communities likely exist in pockets deep within the seafloor, sealed away from the ocean above. These unseen organisms may hold clues to the earliest forms of life on Earth, yet their full diversity and behavior remain hidden. Even larger creatures leave mysteries behind. Sound recordings capture faint movements and patterns that do not match any known species. Some pulses echo like distant steps. Others resemble rhythmic motions unlike whale calls or tectonic rumblings. These sounds drift across vast distances, yet their sources remain concealed behind layers of water that block sight and distort sound. Whether they belong to known animals behaving in unfamiliar ways or entirely unknown species remains an open question. The geology of the trench holds its own silent complexities. Beneath the soft sediment lies a dynamic world shaped by forces that act too slowly for human senses to perceive. The descent of one tectonic plate beneath another is not smooth. It occurs through countless small shifts, fractures, and reconnections. Instruments left on the seafloor sometimes record vibrations that last only moments, too faint to be noticed at the surface. These microquakes reveal patterns of stress, heating, and movement deep in the crust. Yet many geological features defy easy explanation. Some regions of the trench contain unusually warm patches, slight but detectable, suggesting chemical reactions or geothermal activity beneath the sediment. Other areas show ridges and bumps that shift over time as if the floor is slowly breathing. The deeper layers may hold minerals that form only under extreme pressure, shaped by conditions similar to those in the Earth's mantle. Each sample brought up offers surprises, but each surprise opens new questions. Perhaps the most mysterious parts of the trench are the unexplored side passages and shadow zones that branch away from the main valley. These regions appear faintly on sonar maps, emerging like half-seen shapes behind a curtain. Many are so deep and narrow that no vessel has ever entered them. Their walls may hide cave-like structures or steep drops that extend beyond known limits. Some may contain pockets of water isolated from the main ocean, their chemistry untouched for centuries or even millennia. These side trenches may harbor unique ecosystems, perhaps shaped by conditions slightly different from the main trench. They could also reveal geological processes that remain invisible elsewhere. Yet entering them requires navigation more precise than any current robot can manage. Strong currents, unpredictable slopes, and silt that rises like mist with a single disturbance make these areas difficult to reach. And so they remain dark corridors, waiting in stillness. Shadow zones, where sound scatters unpredictably, hold their own mysteries. Sonar pulses that enter these regions return with echoes too faint or confused to interpret. A robot traveling through, one might lose its bearings entirely. What lies within these zones could be nothing more than featureless terrain, or it could be something more complex, carved by geological forces that have not yet been witnessed. The deep does not reveal such features easily. Even the deepest known point, a narrow basin often described as Earth's lowest place, may not be the true deepest location. Small pockets could exist that dip even further, hidden behind slopes too steep to map accurately. Until our tools improve, these hidden depressions will remain possibilities, waiting for confirmation. All these secrets linger in the dark, not out of resistance, but out of distance, depth, and the simple nature of a world shaped by quiet extremes. The abyss does not hide intentionally. It simply holds its stories in a place where our current abilities, for now, cannot reach. And so we continue our gentle descent through the unknown, gathering what we can, learning what we are able, and listening for the faint signals of a world still waiting in the silence beneath the waves. As our long and gentle journey through the deep reaches its final moments, the ocean seems to settle once more into its quiet rhythm. The pressures, the darkness, the drifting clouds of silt, the strange physics of life without sunlight, all of it folds softly back into the stillness from which it rose. We have wandered through layers of a world that almost never meets the surface, a world shaped by slow forces and ancient chemistry, a world where light does not guide the way and sound bends into unfamiliar paths. Each section carried us a little deeper, not only into the trench itself, but into the realization that Earth is far more mysterious than it often feels. For all the tools we build and all the vessels we send downward, the ocean continues to remind us that our understanding remains brief and incomplete. It holds landscapes older than memory, creatures shaped by pressures our bodies could never withstand, and chemical realms where life learns new rules. Even after every expedition, the map of the deep looks nearly as blank as it did before the first dive. We gain faint outlines and glimpses, but the true shape of the trench and of the countless worlds within it stays hidden behind layers of depth and time. There is a quiet humility in recognizing how little we have uncovered. At the surface, Earth feels well known. Mountains have names, rivers have paths, continents lie visible from space. But the deeper we descend, the more the planet reveals how young our knowledge truly is. The Hadal zones, those narrow pockets carved by the slow slide of tectonic plates, are still mostly untouched. Entire branches of the seafloor have never been seen. Organisms thrive in conditions once thought impossible, leaving behind clues that challenge the boundaries of biology. Every discovery only opens more questions, drifting gently into the dark like specks of sediment falling through still water. In this quiet reflection, another truth emerges, something soft yet striking. We send spacecraft across the solar system. We map the surfaces of Mars and the Moon with detail far sharper than any map of our own seafloor. Probes have traveled beyond the edges of the heliosphere, carrying messages for any who might someday find them. Yet here on Earth, the deepest parts of the ocean remain cloaked in shadows, unmapped and largely unknown. It is one of the great paradoxes of human exploration. Space, vast as it is, has become easier for us to chart than the world beneath our own waves. The reasons are rooted in physics, pressure, and darkness, in the way seawater bends sound and steals light, in the crushing weight that presses in from all sides. Space is cold and empty but predictable. The ocean is cold and full and restless, shaped by forces that change moment by moment. In space, a probe can drift for years. In the deep, a few meters can overwhelm even our strongest machines. And so the trenches wait patiently, revealing only what our technology can survive long enough to witness. Still, there is something comforting in this hiddenness. It reminds us that our planet is alive, dynamic, and full of secrets that endure even in an age of satellites and sensors. It reminds us that discovery is not finished. It hints that new creatures, new minerals, new forms of chemistry, and new geological wonders may still rest where no light has ever touched. As we close this journey, I want to gently invite you, the listener, to add your own quiet thoughts. In all this darkness and pressure and drifting silence, what do you think might still lie in the deepest frontier of Earth? Perhaps a creature shaped by forces we barely understand. Perhaps a geological chamber sealed for ages. Perhaps something entirely outside what we have imagined. Your reflections become part of this soft exploration, a way of drifting deeper through curiosity. And if you have enjoyed traveling through these calm and quiet stories, you are welcome to linger in this little corner of science again. Subscribing helps this gentle journey continue. It brings more slow and thoughtful explorations of the strange and beautiful world we share. Thank you for drifting with me through the depths. The ocean rests now, and so may you, knowing that there are still wonders waiting far beneath the waves.